Okay, good morning, everyone. I'd like to call the meeting of the Scientific Review Panel to order. Welcome to everyone on the webcast. Welcome to everyone here in person. Let's just go around the room and state your name and affiliation. I'm Court Anastasio from UC Davis and chair of the panel.
Beata Ritz, epidemiology from UCLA.
Paul Blanc, occupational and environmental medicine, UCSF.
Mike Kleinman, air pollution health effects lab at UC Irvine.
Lisa Miller, UC Davis School of Veterinary Medicine.
Joe Landolf, Departments of Molecular Microbiology and Immunology and Pathology, and member of the USC Norris Comprehensive Cancer Center. I work in the molecular mechanisms of nickel, arsenic, chromium, and PAH carcinogenesis at the University of Southern California.
Stan Glantz, UC San Francisco. I run the Tobacco Center, and I'm in the biostatistics seat.
Kathy Hammond, University of California, Berkeley, Environmental Health Sciences, School of Public Health.
Morning, I'm Ahmad Basaratinia from Preventive Medicine Department, University of Southern California, and I'm a cancer biologist.
Great, thank you, everyone. A few administrative items. Restrooms, drinking fountains are out the doors to your left. If there's a fire alarm, please exit down the stairs and proceed out the building. We have a very clean record on fire alarms, so let's hope we keep that up today. Two major items on the agenda today for this meeting. The first will be a review of the proposed cancer inhalation unit risk factors for cobalt and cobalt compounds. And the second is a review of the proposed updates to the chemical list in Appendix A of AB 2588 air toxics hotspots emissions inventory criteria and guidelines regulations. So we'll do the cobalt before lunch, have a break for lunch in-house, and then we'll do the AB 2588 after lunch. Which brings us, one reminder, please when you're speaking, turn on your mic, get your face close to the microphone for our favorite court reporter, Jim. We'll be making the transcript. And also people on the webcast, it's difficult to hear if you're not speaking directly into your microphone. Okay, which brings us to major agenda item 1, our review of the proposed cancer inhalation unit risk factors for cobalt and cobalt compounds. So this document was from the Office of Environmental Health Hazard Assessment, which went through public review and comment during 2018. The document was revised and the Scientific Review Panel draft was sent to us to review. It was also posted on OEHA's webpage for the public. Today we're going to hear a presentation first from OEHA staff on the proposed cancer inhalation unit risk factors for cobalt and cobalt compounds. Then we'll have our panel discussion and the feedback we'd like to give to OEHA staff. So I'm going to turn it over to John Boudreau from OEHA. Take it away, John.
Good morning. My name is Dr. John Boudreau. I'm chief of the Air Toxicology and Risk Assessment section at OEHA. I'd like to introduce Dr. Darren Dodge. Dr. Dodge is the lead author on the cobalt cancer document, and he'll be making the presentation today on both the document itself and the response to public comments. Dr. Dodge?
Thank you, Dr. Boudreau. Okay, I'm moving on to slide 1 here. Elemental cobalt is number 27 on the periodic table. It's one of a number of transition metals. Transition metals, many of them, can generate reactive oxygen species in biological systems. And this is thought to be a major, if not the main, factor for its carcinogenic action. Uses, there's a number of uses for cobalt. List a few of them here. One of the major ones is cobalt metal powder is used as an alloying component in hard metal. Cobalt oxides and salts are used as pigments in glass and ceramics. And it's found as a component in lithium in nickel-based rechargeable batteries. In slide number 2, ambient air levels of cobalt. They're pretty low. Rural and wilderness areas of California, you see levels of 0.0005 to 0.005 nanograms per cubic meter. However, levels in urban areas are relatively higher than that. In Southern California, mean levels you can find 1.3 to almost 9 nanograms per cubic meter, with maximum levels, highest levels measured as about 3 to 5.6 nanograms per cubic meter. Now, I want to add here that under our hotspots program, we're looking to avoid emissions from facilities that are blown off-site and into neighborhoods, adjacent neighborhoods, or where people work. So if a facility is emitting cobalt or any other pollutants, the concentrations at these neighborhoods immediately off the facility off-site location, the concentrations could be higher than what you're seeing here in this example for Southern California.
Just as a question, a clarification there. So what you're saying is those do not represent measurements around hotspots?
Yes, that's correct. Slide number 3. The bioaccessibility of the cobalt ion is considered an important factor for carcinogenicity. The inhaled cobalt compound particles that are water soluble, and for our purposes, for WEHA's purposes, we're talking about greater than 100 milligrams per liter, will dissolve in the alveolar lining fluid and release cobalt ion there. However, something different is going on with insoluble cobalt compounds, which we define as less than or equal to 100 milligrams per liter. These water-insoluble cobalt compounds will be inhaled and reach distal airways, alveoli, and be uptaken by pulmonary cells by endocytosis. They then dissolve intracellularly in the acidic environment of lysosomes. This process for insoluble cobalt compounds appears to be the reason why insoluble cobalt compounds have a greater cancer potency, which I'll get to later. That is compared to the soluble cobalt compounds. Next slide is number 4. This is just a list of a few of the commercially important cobalt compounds and their water solubility. In the first row, I show cobalt metal particles with a water solubility of 2.9 milligrams per liter. So that's well under our definition of water solubility. 100 milligrams per liter, anything under that is considered insoluble. The next two compounds are the sulfate and the chloride, and that water solubility is considerably greater than 100 milligrams per liter. And the last two are the cobalt oxides, and those are well under 100 milligrams per liter. In other words, our cutoff of 100 milligrams per liter as to whether a compound is considered soluble or insoluble works well for this sort of scheme. Next slide. Now going to some of the toxicokinetics. There are a number of acute human studies, short-term studies, and what you see is a multiphasic elimination of inhaled cobalt metal or oxides from the lungs. The initial phase is a rapid phase. The half-life is 2 to 44 hours, and that's primarily due to mucociliary clearance. And there's an intermediate phase of 10 to 78 days half-life. That's primarily due to macrophage-mediated clearance. And then there's a fraction of inhaled cobalt, which is retained long-term on the order of months or even years. And that's due to what is thought to be cobalt bound to cellular components of the lung. With short-term exposure, cobalt did not translocate or accumulate appreciably in other tissues with acute exposure. There are next slide, there are toxicokinetic studies that look at long-term exposure, and this was performed by the National Toxicology Program, which I'll call NTP from now on. They conducted 13-week and 2-year inhalation studies with cobalt metal dust in rats and mice. Their main findings: cobalt concentrations and burdens in exposed rats and mice increased in lung and all other tissues examined, indicating absorption and systemic distribution occurs following inhalation. Next point, our next finding, lung cobalt concentrations and burdens in rats and mice increased with increasing cobalt concentrations, but appeared to reach a steady state about day 26 into their 13-week and 2-year studies. And finally, cobalt burden steadily decreased following cessation of cobalt exposure. Slide number 7. Continuing on with their findings, cobalt concentrations in rats showed the following order: greatest in lung, followed by liver, kidney, femur, heart, serum, and lowest in blood. And these findings were similar in mice too. Overall, normalized lung tissue burdens, measured as the ratio of tissue burden to exposure concentration, did not increase with increasing exposure. Next slide. Now we'll go on to the carcinogenicity of cobalt compounds. The NTP performed an inhalation cancer bioassay in rats and mice for cobalt sulfate heptahydrate in 1998. They then followed up with a inhalation cancer bioassay with cobalt metal dust in 2014. The carcinogenicity findings for cobalt metal dust, we use BioWeHA as the basis of the cancer potency factors for cobalt metal and all insoluble cobalt compounds. And this is for cobalt compounds with a water solubility less than or equal to 100 milligrams per liter. The carcinogenicity findings for cobalt sulfate heptahydrate will be used by BioWeHA as the basis of cancer potency factors for soluble cobalt compounds. Again, this is for water solubility greater than 100 milligrams per liter. So these were 2-year studies. For cobalt metal, they use F344 intact rats and B6C3F1/N mice, 50 animals per exposure group per sex per species. The concentrations were 0, 1.25, 2.5, 5 milligrams per cubic meter. Exposure duration was 6.2 hours per day, 5 days a week, for 105 weeks. For the cobalt sulfate heptahydrate study, or assay, they use a slightly different strain of rats and mice, but the exposure groups were the same size, 50 animals per group, per sex per species. Concentrations were a little lower in here, 0.31 and 3 milligrams per cubic meter. The exposure duration was the same in both studies. In other words, it was 6.2 hours per day, 5 days a week for 105 weeks. Slide number 10. Let's go over the tumor incidence findings after 2 years of exposure to cobalt metal dust, first in the rats. The main finding is increased lung tumor incidences in male and female rats, alveolar, bronchiolar adenoma, and carcinoma combined. The results, the tumor incidence results, you see a statistically significant increase in these types of tumors in all exposed groups. 1.25, 2.5, and 5. And that's in both male and female rats. In addition, there was a positive trend for this tumor type. In other words, as the dose goes up, you get an increase in tumors. Now, also in rats, you saw other types of tumors. In rats, you see an increase in adrenal medulla tumor incidences. This is specifically, this is benign and malignant pheochromocytoma. The increase was at the mid and high dose groups in both male and female rats, and there was a positive trend for this tumor type too. And there were still more types of tumors found in rats. In male rats, there was an increase in pancreatic islet cell adenoma and carcinoma at the 2 highest dose levels. In female rats, you saw an increase in mononuclear cell leukemia in all exposed groups. Now let's talk about the tumor incidence data in mice. In both male and female mice, there was only one type of tumor found that had increased, and that was alveolar bronchiolar adenoma and carcinoma, similar to what you saw in the rats. And as with the rat data, you saw an increase in these tumors in all exposed groups. Now, in the 2-year cobalt sulfate heptahydrate assay or study, the tumor incidence in rats, you also saw an increase in lung tumors, although the response wasn't as strong. In male rats, there was an increase in this tumor type at the high dose group of 3.0 milligrams per cubic meter. In female rats, there was an increase in the 2 highest dose groups. And the next slide here, you also saw an increase in pheochromocytoma, as you did with the rats in the cobalt metal study. However, this response, again, was not as strong. Female rats, you did see an increase in this tumor type at the high dose group, but in male rats, the data was what the NTP calls equivocal evidence. And that's because the increase was only seen in the mid-dose group, a statistically significant increase, but not at the high-dose group. And then there was no positive trend for this tumor type, so they gave it the equivocal evidence. Now, in mice, again, there was an increase in lung tumors. In male mice, the increase was only observed in the high dose group, and in female mice, it was in the 2 highest dose groups. And as with the cobalt metal data, you only saw an increase in tumors in the lung of mice. You didn't see it in any other organ system. So what other evidence is there for cancer resulting from cobalt exposure? There was only limited data for epidemiological studies, the best of which was by Sani et al. In 2017. And this was a retrospective study at a Finnish cobalt plant. The N was 995, which is pretty high for a epi study. But this included all employees that worked at the plant for at least 1 year or more. They did have a mean follow-up of 26.2 years. The airborne cobalt concentrations at the plant, it mostly was as the sulfate or metal dust. They measured several times per year. Concentrations range from 0.1 to less than 0.02 milligrams per cubic meter. What the workers were exposed to really depended on the job type or department they were in at the facility. The results were that they saw no increase in cancer risk with 5 years of employment at the facility. This was based on a standardized incidence ratio, or SIR. The so-called control group was Regional Finnish Cancer Database. An SIR of 1.08 for total cancer risk suggests they were no different than the control group, or not much difference in total cancer risk. What's interesting here is that for the workers, the SIR was 0.52. That was specifically for lung cancer, and this would suggest that the workers actually had less lung cancer than the control group. Authors couldn't explain it because there was no difference in smoking. Kind of just left it at that. There were some issues with the study. The authors noted that there were respirators available, but not mandatory to use. So it was unclear from the study how often the workers were using these respirators. We don't actually know what the true exposures were in many of these workers. They didn't have a mean exposure time for the group of workers either. They only presented data as employed at the plant for at least 1 year or for 5 years.
Dr. Hammond, I think you had a question.
Yes, thank you. This is good. Yeah, I don't know the answer, but I'll ask it anyway. The question is, did they do an analysis by milligram per cubic meter years of exposure? I mean, you're saying that clearly there was a difference by the jobs in the exposures, and in many facilities, 90% of the workers might have low or no exposure. And so looking just at that, all workers compared to the neighboring area might not have any meaning unless they've at least categorized the jobs or some milligram per cubic meter individual years. But did they do that?
I'm pretty sure they did present the data as milligrams per cubic meter years.
They did?
They did not.
Yeah. I mean, so I think it's one has to be careful how much we can deduce from the study if we
Correct,
don't know
yeah.
what percentage of people had any kind of significant exposure.
I actually think I know why they don't see anything and why they see such weird numbers. All you have to do is look at their table 1, and you see that the bulk of their workers were between 15 and 29 years when they were employed. So how many years do we have to wait before we see lung cancer or any other? 26 years isn't enough. Yeah, but still, if most people are around 22 or 3,
Yeah, that's back to like the diesel study, going back many decades, where 10 years after exposure, you saw nothing. You had to be at least 20 years out. So I think it's important. You're right to point all these out, yeah.
Okay, I'm moving on to the next slide. Other evidence of cancer due to cobalt exposure comes from genotoxicity studies. There was a considerable database of genotox studies for soluble cobalt compounds and cobalt oxide compounds. So this includes the DNA damage assay, or COMET assay, oxidative DNA damage assay, in vivo DNA adduct assay, bacterial and mammalian gene mutation assays, chromosomal aberration assay, and the micronucleus assay. Now, these were mostly positive findings for genotoxicity among all these assays, with the exception of the bacterial and mammalian gene mutation assays. Those are primarily equivocal or negative. There are a few genotox studies for cobalt metal dust, where they looked at DNA damage assay or COMET assay, in vivo oxidative DNA damage assay, gene mutation analysis, bacterial mammalian gene mutation assays, chromosomal aberration assay. Positive genotox findings included results from the COMET assay, oxidative DNA damage, and gene mutation analysis. And again, there wasn't a lot of positive results from bacterial mammalian gene mutation assays. Next slide. So overall, the cancer hazard evaluation here, based on lifetime NTP inhalation studies for both the cobalt metal and the sulfate heptahydrate. Cobalt is carcinogenic in multiple species, that includes rats and mice. Cobalt induced lung tumors that were of the same histogenic type in both species. Cobalt induced tumors at one or more sites in both rats and mice. In addition, there was numerous positive genotoxicity studies. Combined, these factors point to a strong potential for cobalt to induce tumors in humans as well. And next slide. Now I'll go into the cancer slope factor derivation. The first step in the cancer slope factor, or CSF derivation, is converting the NTP tumor incidence into what's called the effective tumor incidence. The effective tumor incidence is the number of tumor-bearing animals over the number of animals alive at time of first occurrence of the tumor. This removes animals from the assessment that died before they are considered at risk for tumor development. Now, I just give this table as an example. This is a comparison of the NTP tumor incidence with the effective tumor incidence for rodents exposed to cobalt metal dust. So the NTP tumor incidence is the second column from the right. The denominator, you see 50 animals per exposure group. Well, at least in most cases. Sometimes it's less than 50 because an animal died due to some accident that had nothing to do with the exposures. So they reduce it to like 49 rather than 50. And then the effective tumor incidence is the far right-hand column. You see that the denominator often is less than 50. It's reduced by 2 or 3 animals in most cases. And so it reduces it a little bit. And what this gives you an indication of is that, at least with regard to these types of lung tumors, they were showing up early, like in the first year of exposure in the study. So not many animals died prior to the appearance of this tumor type. Next slide. So now we have the effective tumor incidence. We also need to convert the air concentrations to an average daily dose. And that's in milligrams per kilogram body weight per day. So this equation is shown here. Dose is equal to inhalation rate times concentration over body weight. Concentration is time adjusted to an annual average. The exposures were 6.2 hours per day, so this is 6.2 over 24 hours. Exposures are 5 days a week, so this is 5 days over 7 days. Body weights used, it's an average over the 2-year exposures. The NTP measured body weight on a weekly basis during the first year of the exposure, and about every 2 to 4 weeks during the second year of the exposures. So that's how the average was determined, average body weight. The inhalation rate is based on the body weight of the animal. Body weight, there's a good relationship between body weight of a rodent and its inhalation rate. So we have these equations down here at the bottom next to the bullets, one for rats and one for mice. So we use these equations to determine the inhalation rate based on the body weight of the animals. So using the dose equation here, we converted the cobalt metal chamber concentrations to an average daily dose, and this table just shows what the average daily doses we used for the rats and mice. So now we have the fraction affected, the effective tumor incidence, and the dose. So now we can run the multi-stage cancer model in the benchmark dose software, US EPA's benchmark dose software, to determine the cancer potency. Potency values derived using the we derived potency values based on a benchmark response, or BMR response rate of 5%, to calculate a benchmark dose. The 95% lower confidence bound on the BMD, or benchmark dose, is used to calculate the cancer potency. So the cancer slope factor, what we're looking for here is simply 5% or 0.05 over the BMDL, which is the 95% lower confidence bound on the BMD. We determine cancer slope factors from all the tumor types that were found, individual tumors. This included the lung tumors in all rats and mice, both males and females. As you may recall, we saw pheochromocytoma in male and female rats. Male rats also had an increase in the pancreatic islet cell adenoma and carcinoma, and you saw leukemia increase in female rats. So we developed cancer slope factors, or individual cancer slope factors, for all these tumor types. So plugging the data into the benchmark dose, or BMDS software, using the multi-stage cancer model, we get a plot fit to the data. In this example, this is the lung tumors in male mice exposed to cobalt metal. So what we have on the x-axis is the average daily dose, which I showed you how we calculated earlier in the earlier slide. And the fraction affected is the y-axis. That's the effective tumor incidence there, which I showed you how we came up with in the earlier slide. So the data points are shown in green with the error bars. In the lower left-hand corner, that's the control group. And as you go up and to the right, you get your low-dose group, mid-dose group, and your high-dose group at the upper right-hand corner there. The benchmark dose software fits a line to that data, which is shown in red. Now, we also plugged into the model that we wanted the benchmark response rate of 5%. In other words, we want to define the 5% response rate, the increase in this particular tumor type over the control group of 5%. The benchmark response rate gives us a BMD, or benchmark dose. That's the vertical black line in the lower left-hand part of the graph. It's right next to the BMDL. So it looks like one solid line to me from here. But anyway, they were very close together in this particular graph, the BMD and the BMDL. So the dose, or average daily dose, that you get at that BMDL, where it intersects the x-axis, that gives you a dose, and I believe it's around 0.011 milligrams per kilogram per day. So the cancer slope factor is basically just 0.05 over the BMDL of 0.011 milligrams per kilogram day. Now, before I go on, let's see. Okay, well, rats develop tumors in more than one organ system. So before I go on to show you more of the cancer slope factors we devised, we got to note that rats develop tumors in more than one organ system, and basing cancer risk on only one tumor type may underestimate the tumor risk. So we used what we call the MS combo model in US EPA to come up with multi-site tumor cancer slope factors. So we used the model to combine the lung, adrenal medulla, and pancreatic islet tumors combined for male rats, and in female rats, we combined leukemia, lung, and adrenal medulla tumors. Now, the final calculation we need to do is to extrapolate to humans, because this is rodent data. So we take the animal cancer slope factor we came up with and go to extrapolate to cancer slope factor human equivalents, and this is done by using body weight scaling, body weight to the 3/4 power. And this equation is shown here in the middle of the slide. The human cancer slope factor is equal to the animal cancer slope factor times the body weight of the human over the body weight of the animal to the 1/4 power. This interspecies scaling factor is used to account for pharmacokinetic differences as well as for pharmacodynamic considerations. Now in this table, this is the major findings of cancer slope factor for each male and female rat and mouse. So in male rats, the highest cancer slope factor we got was, of course, when we combined the various tumors found in male rats. And the cancer slope factor, the human cancer slope factor, is the column on the far right. It was 22.17 milligrams per kilogram day to the -1. For female rats, we combined the tumors found in female rats, and we came up with 10.7. Male mice, as you recall, tumors were only found in the lung. However, it was a pretty strong response, and that actually resulted in the highest cancer slope factor of 27.49. So among male and female rats, male and female mice, the most sensitive species here is mice. Most sensitive sex is males. So this cancer slope factor is what we use to represent the cancer risk from cobalt metal. However, there was a bit of a hitch here. US EPA came out with the updated version of their benchmark dose software after we first came out with this data, this analysis. In their software, they actually gave recommendations as to the BMR or benchmark response that is used in their model. Now I'm showing this graph I showed you this graph several slides ago. This is, again, the lung tumors in male mice, the benchmark dose software. It shows the data there for control, low, mid, and high dose, and then the line that was the plot fit, or the line fit to that data, resulting in a BMD and BMDL at the lower left-hand end. So the new version of the software now gives recommendations as to the BMR. In this new software update, a 5% BMR resulted in what's called a questionable recommendation. This is because the BMR chosen was 3-fold lower than the lowest non-zero dose, and the BMDL was 10-fold lower than the non-zero dose. So what we did is okay, I can try and repeat that. The new benchmark dose software that US EPA came out, a new version, new update, now has recommendations as to how the benchmark response is fit to the line, whether it's adequate fit, questionable, or unusable. They didn't do this before. They just kind of left it open. So what they're saying here is that a 5% response rate plugged into their software results in a questionable recommendation because a 5% response rate is outside of their is beyond the area of, I forget what the term is, but it's just too far away from the lowest non-zero dose. The lowest.
Is essentially what the software has concerns about the EMDL being out too far outside the range of observable data.
But that
You know,
is
it's-
really a function of the fact that you had very positive results even at the lowest dose. So I don't, you know, yes, it's outside of strict guidelines, but you're dealing with something that has a very steep onset curve.
Correct.
That was exactly my point, Kathy Hammond. That all the doses were over 80% of the animals. I mean, I remember there's like 47, 48 of the 50, got cancer. So I think it's important to think of be clear what's questionable. There's no question that it's causing cancer, that it's potent. The question is just what is the dose where you get a 5% increased risk? And certainly it's really hard to calculate that given that kind of response, but I think it's important to be clear. There's no question about the cancer risk.
But go ahead.
I find that very suspicious that a software package is giving you a qualitative statement about data. Isn't that something that experts like us should be deciding?
That's what I guess the editorial judgment that US EPA chose to make.
Well, I met with the. I mean, you guys have stolen my punchline.
Yeah, let the biostatisticians speak.
So I met with them yesterday to talk about this, and I think that I agree with you. I mean, the software is making an arbitrary decision that's stupid, and I think it should be ignored. And I mean, if you look, I mean, they're right that the lowest exposed group is quite a lot higher than zero, so there is that big gap. But you do have a zero exposure control group too, so the estimate is not outside of the range of the data. And as Mike said, I mean, if you look at this graph, probably it's underestimating the slope of the curve at low doses. So it's probably way underestimating the actual cancer potency at the bottom. Now, the problem is you don't have any data down there, and so you don't know. But I mean, my recommendation is that they just stick with the 0.05 estimate coming out of the program. Say that there's uncertainty here because there's that, they didn't expose any animals down, with a low exposure, but that they should, that whole thing about the software is unhappy should just be dropped out of the report. You should use what it came up with, but then put a strong statement in that almost certainly is underestimating the cancer potency at low doses. I mean, for exactly the reason that Mike said. So this isn't, by the way, in this cadmium, or pardon me, cobalt sulfate thing, this isn't a problem there because they have data down at the low, they have data where rats were exposed at lower levels. But I found that was all very confusing to me, and I think what they did is, I mean, it's not, as a general principle, a bad thing to say it would have been nice to have had more data at lower exposures. But I think because some software programmer programmed that, that's not a reason to make policy here. And I think we need to strongly say this is probably underestimating the risk. I think it's the best you could do with the data you have, because if you start coming up with some alternative formulation for the shape of the curve, which is, what you would need to do, that's going to be arbitrary too. So I think using the standard protocol that you did to fit the curve is fine. But anyway, but I think you have like 1, 2, 3, 4 people who all independently came up with the same conclusion, which is pretty strong.
Paul Blanc, but there actually could be other sensitivity analyses you could do with the data that you have that might reassure you about the dynamics or shape of this dose response. And two thoughts that come to mind immediately. One is that since you're not looking at multi-site cancers with the mice, but only looking at the lung cancer relationship, that's correct? I understand
Correct.
that. For comparative purposes, it might be helpful to see what your dose response looks like for lung cancer only in the rats, since biologically they should be behaving similarly. That's one thing, because you make the argument that on general principles, multiple cancers should be combined as the endpoint because that will be more sensitive. But I'm not sure that that's what your data would show. And secondly, there is a phenomenon here where the data for actual lung cancer and not lung cancer plus lung adenoma are cleaner, in that there's no spontaneous lung cancer in the control rodents, at least in the rats. It's 0, right?
I think you're correct. Yeah, the rats may have not had as much
Right.
of a spontaneous
So
tumors
again,
as the mice did.
Perhaps not as your main analysis, but as your way of looking at how the data perform. You may find that your estimate has less issues with it if you actually look at the cancer, even though you make the argument that it's more sensitive to combine the cancer and the non-malignant tumors of the lung. I don't know if that would be the case, but I could imagine looking at different scenarios as a way of saying, look, this is all going in the same direction. There's not an order of magnitude difference between the estimates we're getting for the cancer slope. And that might reassure you that some of the challenges you're facing with this steep takeoff are can be discounted. I'm not sure that would be the case, but it potentially might be worth you looking at that. Also, by the way, is it such a violation to combine the male and the female rats and the male and the female mice? Because they're all behaving the same way. It seems like you're greatly reducing your power to make an accurate estimate by
Yeah, but the problem that's all reasonable. But the problem they have is just like if you go back to slide 9 or 10 rather. So if you look at the tumor incidence between 0 and the lowest dose, it goes from 2 to 25. Well, this is just the lung cancer.
This is both the adenoma and the carcinoma. That was actually my point about what when you look at the carcinoma, which is in the main document. I don't know what page, but
So if you go to 14, so what's 14? Is that the one you said, Joe? So that's to my 15.
Oh, these are sulfate.
Oh.
You want to do metal, don't you?
I think it's in the main document, not in the slides.
Well,
Yeah,
13.
page,
Page 55 in the main document.
I think just to say, I think kind of what we're thinking about, if I'm understanding my colleagues, but that it may be that because there's this high background level, that we're starting with 16 out of 50 in the group that you're using for analysis, it might be that if you were to use another species, it might be worthwhile seeing. I mean, I think that we could come away from what you've shown to say, originally, we're starting this, that whatever estimate we have has a high risk of being not sufficiently protective, that we've underestimated the potency, as you've said. But it might be worth trying to check the potency with the rats as opposed to the mice, because there's less of that background and therefore maybe less of that error. And then if it shows it may not show this as low a number. If it doesn't, we know that the mice are more compelling then. But it might give us better information. I guess I would love to just see what that came out to. If you did the dose response for the rats, male rats as opposed to the male mice. The male rats having the background 0 dose of 2 as opposed to 16 out of 50. I can't look at this and know how it would come out. I'm
No.
sorry.
Remember, we adjusted the inhalation rates based on the body weights of the animals, and we used two different equations for rats and mice. We update the OEHA, our agency, updated that information because we have a lot more recent data on the body weight relationship to inhalation rate. We got I think we did a good job in coming up with a better equation than what was used, which was, 35 years old. We only had time to do that for the rats. That had quite an effect on the cancer slope factor, though, because we had used Anderson 1983 equation for rats. So that caused a difference, because for mice we used the old equation. That's all we have at the time. You also have to take into account we're extrapolating humans from a smaller animal from mouse. So you get a larger difference larger increase in the slope factor. So I understand what you're saying, just looking at incidence rates, how it looks like the rats should have a bigger response, but in our extrapolation from inhalation rate, yeah, it does affect it. Look like the mice are much more sensitive than they maybe truly are.
Yeah, and then I'll stop and give Joe a chance. But none of this, though, is going to deal with the problem that your lowest positive exposure is a lot. You have a big response in all of the data at the lowest non-zero exposure they looked at. And so you don't have any direct data with which to estimate the curvature of the line between 0 and that dose. And the slope is very dependent. I mean, it's at near 0 is going to heavily depend on that. So I think that you're just kind of stuck unless somebody goes and gets some more data. But it's very clear, I think, that I think you should do it the way you did it, but I think we need to say that you are almost certainly underestimating the potency. Like if you took the data, if you just somebody suggested a sensitivity analysis, and you just go back to the slide with the curve on it. One thing you could try just for kicks is to fit that with a saturating exponential. and you're going to get a really steep slope at the low levels. But the problem is that that slope is effectively going to be determined by the upper doses where there's not that much difference. So that's going to, it'll be a much bigger slope, but it's also going to be kind of unreliable too. So I think you have the problem is you just don't have data to fill in that hole. I'll be quiet.
Being an epidemiologist, we usually would not estimate this in a cohort according to the lifetime rate, but something like a Cox model, time to event. And I heard you saying that these mice or rats actually got their tumors early. That's why nobody else died, right? So given that they got the tumors early, they had no time to those and almost every one of these animals developed a lung cancer. We really don't know what's happening at lower doses when they don't develop lung cancer that kills them off in terms of other organs. So I would actually be quite concerned that there might be effects on other organs that we're just not seeing because they would be showing effects later. One comes to mind because the alveolar clearance here, where does that go? The mucus, it gets swallowed, right? So it goes in the GI tract. Also, these mice and rats probably lick themselves, and aerosolized exposures are on the fur. So I actually would really like to see, but I know we don't have them, but I would like to see lower dose studies and other organ systems.
Yeah, well, I think part of the problem here is when NTP did the cobalt metal study, they were looking back at the cobalt sulfate study and thinking, well, cobalt metal is going to be less potent, and they wound up with a big surprise. I mean, they essentially said in the document they were surprised. So that's where part of the problem's coming from, but it's really not likely that anybody else is going to repeat this study. I mean, NTP is one of the few people that are, if only, doing inhalation cancer studies these days.
Yeah, a couple comments. First, thank you for all your work. It's a huge amount of work. I appreciate it. In looking at that curve, that you have up there, I mean, one of the questions, a couple of questions occurred to me. One is it linear from 0 up to some dose, and then is it response saturating for some reason? Or the other one is it a different function entirely than a linear that saturates? And I would discuss that concisely in your report so that you let people know we're a little bit curious about that shape of the curve. The other thing is when I was reviewing this, the whole thing sounds a lot like nickel carcinogenesis to me. There's tremendous parallel between the two. I've worked on nickel carcinogenesis since 1983. And the insoluble nickel compounds we call them phagocytosed, the particles from 1 micron up to 10 or something like that. And because when you phagocytose these particles, you can see them under the light microscope, you get a real bolus of nickel into the cell. So if it were all to dissolve, it would be millimolar, and sometimes the cells pop from osmotic shock. And this sounds very much like that. And the insoluble compounds are much, much more toxic and more carcinogenic than the soluble ones. The soluble ones really are not very carcinogenic at all, because you get that bolus into the cell by phagocytosis. And then the other point is very interesting. I was reading this, that there's some thought about oxygen radical generation, which has gradually been creeping up over the years. But not a lot of real certainty about mutagenesis. And it turns out with nickel, we're getting ready to publish a paper now, the nickel is not positive in any of the classical mutagenesis assays for mutation wild being resistance, mutation 6-thioguanine resistance. But we hit a home run. We sequenced the whole genome of the nickel transformed cells. And guess what? There's all kinds of chromosome amplifications and deletions, and there's point mutations all over the place. So there's something interesting going on with these oxygen radical generating agents like nickel and like this cobalt that still needs to be ferreted out. It's been very interesting.
Yeah, there's similar studies with cobalt showing that particles are phagocytosed and result in up to millimolar concentrations within the cell. Yeah, it's very similar to nickel.
before you go on, we've had this big discussion. I mean, I think, can we, I know we usually make recommendations at the end, but we just finished talking about this. And I'd like to suggest, and I don't know if I want to, I'll move it just so that you delete that discussion of the software telling you what to think and just stick with just the conventional analysis, but highlight the fact that because of these data problems, you're almost certainly underestimating the cancer potency. Don't know how much, but you're almost certainly underestimating it. So I'd like to move that we recommend they do that. Okay?
Well, let me address that for a second. I think you're going to talk in the next couple of slides about your alternative approach, right, which ended up giving a slightly more protective value, a slightly higher cancer slope factor.
Yes.
So it seems to me that we'd rather go with the slightly higher cancer slope
Okay, we
factor.
can wait. Okay, I'll withdraw what I said. But I'll tell you, the problem I have with that is that essentially what they did, if you look in the appendix, is they have the formula, the equation for the line. And then they differentiate it to get a slope, but then they use the parameters from that fit in the calculation. So all of the uncertainties and problems that are associated with the fact that there's no data down, between 0 and the first point are still embedded in that other calculation. So I actually think it's kind of misleading to say that's somehow better. Because it's based on the same information. It's just sort of making a couple of different assumptions, which I think are pretty arbitrary. And basically the 15% number that's rather than using a 5% over the background thing, they're using 15. But as best as I can tell, that was just picked to get it up high enough that the computer program wouldn't complain, which I think is not a good reason. But I'll withdraw with my suggestion. But I hate that other analysis because I think it just it's trying to look different, but every single problem that we've talked about so far with this is it's in the other analysis too. It's just more obscure.
One other point. In your inhalation dose calculation, it looked to me like you were assuming 100% deposition. That you don't take into account that not 100% of the particles will actually deposit in the respiratory tract.
That is a health protective assumption, correct?
But in this case, I don't think it's health protective in that you're calculating your slopes based on a higher dose than actually is. The effects you're seeing are most likely due to a lower inhaled dose.
I get to where you're going with that. The problem is trying to adapt, for example, the multipath particle dosimetry software, trying to adapt that to what we're doing, and nobody's really gotten to that point yet. US EPA's not even doing it with all their squads of particle dosimetry people.
Yeah, no, I'm just amplifying what Stan just said.
Right.
You are coming in with a less than conservative, actually, proposal. So in all likelihood, even though you're getting, and you will be having a slightly bigger slope factor, this, in all likelihood, does not overestimate the risk. If anything, it's underestimating potential risk.
Agreed.
And I think that should be made very clear.
Yeah, I just would like to say, Kathy Hammond, I agree as well. And I think it's very important that we make that point, that where there are problems in the data, and they're not your problems, they're the problems with the experiments, that the errors that they lead to are all errors which underestimate the potency. because there's an underlying assumption of 100% deposition, which overestimates the dose, therefore the effective dose, without knowing how much it's doing it, the effective dose is actually a lower number, following Michael's comments. And similarly, we've got the dose, I don't actually agree with Stan on taking away the designation of questionable, because the software tells you that. I think we need to be honest and upfront with that. But I think we just need to then, after that, say what's questionable is that it could well be that this is underestimating the potency. Not that there's no question whatsoever about the carcinogenicity. And I think it's very unfortunate that NTP didn't look at their data and say, oh my golly, time to do another study at lower doses.
Yeah, of course, the problems of getting more low-dose data are well known. You start getting into the mega mouse experiment that Leanne Russell did at Oak Ridge Laboratory. We're using thousands of mice to get it, so you're having intrinsic difficulties addressing that. But I was looking at this curve, and if you almost took 0 in the first 2 points, you might get a better estimate of the slope. This curve, the slope is changing at every point, clearly. And I think you should discuss that as best you can. You can't fix it at this point unless somebody comes up with a new theoretical construct.
That might be a better way to do it. Well, just do a straight line. That's probably better.
It was 0 in the first 2 points. Yeah, I think that would be more accurate. Tell people why you're doing it.
Thoughts about that idea, Oiha?
We would have to, I mean, we prefer to use all the data we have. We'll drop high doses if necessary if we can't get a good fit. But if we can get a fit, we prefer.
Well, no, I mean, that gets back to I mean, I agree with Kathy. We could leave the questionable thing in there and would say that the thing that makes it questionable is that you're underestimating the dose. But actually, it may be, if you're interested in getting something that's, closer to reality, drawing the straight line between the first 2 points. I mean, if I just drew the line, it's probably not going to make a huge difference, actually. But that might be a way to, do a little bit of a sensitivity analysis. If you just drew a straight line between the first two. But it's clearly the questionable thing about the fit is that you're underestimating the slope at the low doses. There's just no question about that. And in fact, if you look at the residuals, you can see that you're below that, the first non-zero point. The fit is way below that, which is more evidence that you're underestimating the slope at low levels. I mean, whether based on the biology, there would be something you could say is, well, here's the slope we got, and we're going to increase it by a factor of something or another to compensate for all these problems. I don't know if that we could come up with something that would be bendable. But, it's just clear that and again, I don't think that the thing you did next solves the problem. Obscures it.
So this is a parametric model, right? You could just use a spline with a node at the first point to estimate that. Yeah.
Darren, you want to tell us about the approach that Stan hates?
Well, okay. All right, so we're going on to the next slide here. So what we were proposing was that if a BMR of 5%, for example, yields a questionable cancer slope factor, we would use what's called the exact formula for the calculation of the cancer slope factor. And we give this equation here. It's the cancer slope factor is equal to the minus natural log of 1 minus BMR over the BMDL. So this estimate is derived by solving for the beta parameter in the risk equation and inserting the result into the log likelihood equation for beta. To use it to profile the BMD and obtain the BMDL. So the next slide, when we apply the exact formula, we get a constant BMD over a range of BMRs. From 5 to 15%, we got the same BMD. This exact formula appropriately accounts for the increased curvature of the dose-response relationship at higher dose levels and BMRs. Again, well, what I should note here is that in the final bullet, at BMR 15% gave a viable response in the benchmark dose software. So 5% gave a questionable, but we only had to bump it up to 15% to get a viable. That's because the BMDL is now within 10-fold of the lowest non-zero dose. I'm just explaining the US EPA software. So the benchmark dose that, or I should say the cancer slope factor that results from going from 5 to 15% in order to get a viable response really doesn't change much. The cancer slope factor, that is, doesn't change that much. So that's what we're showing in this next table. So the US EPA software, benchmark dose software, their results are kind of in the middle columns there. The cancer slope factors are in bold, CSF column, and next to it is their recommendation. So at a 5% response rate, you get a cancer slope factor that's questionable. Go down to the next row, benchmark response rate of 10% is also questionable. Then you get down to a BMR 15%, and it's viable and recommended. The cancer slope factor doesn't change all that much. It goes from 4.46 to 4.2. Now in the far right-hand column, that's where we apply the exact formula. And you'll see from a BMR 5% to 15%, it gave the same cancer slope factor of 4.57 milligrams per kilogram day to the minus 1. That's what we proposed using.
And kind of to put this into perspective, is what you're talking about is a change in the potency factor of like 5%. You know, we're a long way from order of magnitude differences. So we're kind of fine-tuning this, but in real world terms, these numbers are all falling out to be about the same.
Yeah, well, see, that's another reason to like not do it. Because there's nothing, you're pulling 15%. Basically, you pick 15% so the program wouldn't complain. But that doesn't fundamentally change the data or the problem that you've got. And so I just think you should go with they're all 4.5, you know, less. And anyway, I'll stop obsessing. But 4 of us had the same exact view of reading this without talking to each other.
And you know, it would make me happier if you just did a simple linear least squares fit to the 0 point and the first 2 data points and just put it in a document and say, this is a comparison of what we do, what we get no matter what we do through these 3 different techniques.
Sure,
Just
we can add that. Yeah.
Yeah, that shouldn't be too much work, I hope.
Okay, I'll go on to the next slide here.
Third point, my first 2 data points, you mean the 0 and the first 9?
First 2. Yeah.
Right.
The
Okay.
0 point in the first 2 real.
Well, I wouldn't use the first 2. I would just, because that's going to, again, underestimate. Yeah, but the X values are very different. So you're going to, that's
what I'm trying to say.
yeah, so that's going to give you a lower slope.
Yeah.
So I mean, I think if you want to do it, I would just use 0 in the first point.
Yeah, I hear what you're saying. I'm thinking that the low dose points are also not so accurate, because they're smaller and you have big error bars and all that. So it's kind of a compromise. Do it both ways and just report what you got.
I don't like that either. I think you should just go with the standard approach and say the software highlighted the problem. There's a lot of uncertainty, but one thing we're pretty confident of is the uncertainty is all in the direction of underestimating the risk. Not questionable in that you're overestimating the risk. It's questionable that you're underestimating.
Okay, so I'll go back to this slide, looks like 36. Well, using the exact formula, we come up with a cancer slope factor of 28 milligram per kilogram day to the -1. That's all I'm showing here in this slide, the extrapolation to the human cancer slope factor. Next slide. So, okay, that was just for cobalt metal. We also did a derivation for cobalt sulfate heptahydrate. So we developed cancer slope factors for the lung tumors, for pheochromocytoma. It was in female rats only. Then we also did a multi-site tumor cancer slope factor, combining the lung and adrenal medulla tumors that occurred in female rats. So this will go a little faster because I went into more detail with the metal. We don't have to do so with the sulfate here. Of course, we have to determine the effective tumor incidence, and so that's just a comparison here for in female rats, the pheochromocytoma and the lung tumors. NTP tumor incidence is the column second from the right. Again, it's 50 animals per group unless some animal died early in the study from an accident, and it basically died from some cause not having to do with the exposures. And the effective tumor incidence is over there in the right-hand column. You might notice that these numbers this effective tumor incidence numbers are lower over here for lung tumors compared to the metal study. Probably because, I didn't check, but it's probably because for cobalt sulfate, the tumors were showing up later than they did for cobalt metal. So more animals are dying due to other causes before the appearance of this first appearance of this tumor. Okay, we also had to calculate the daily dose, and this is just a table showing our daily dose in milligrams per kilogram day. And again, that was using the equation up there at the top, the inhalation rate times concentration over body weight. Converting that, the chamber concentrations to a daily dose. And then we plug it into the benchmark dose software. And in this particular example, this is also in male rats, as we showed for cobalt metal, with the lung tumors in male mice. I'm sorry, it's lung tumors in male mice here. And the benchmark dose and BMD and BMDL are shown in the lower left. Those are the vertical black lines. And as you notice, it's situated closer to the lowest non-zero dose there. So we didn't have the issues with the benchmark dose software we did for cobalt metal, where we're getting a questionable response when we used a BMR of 5%. Going on to the next slide, here we look at the highest cancer slope factor we derived in male rats, female rats, male mice, and female mice. As you might expect, the highest cancer slope factor, human cancer slope factor we derived was when we combined the two different tumor types we saw that increased in female rats. That was the adrenal medulla tumors and the lung tumors. When we combine that, we have a cancer slope factor of 13.41. And because this was in cobalt sulfate heptahydrate, we need to normalize to the cobalt content in the sulfate heptahydrate. This is because the cobalt ion is considered to be the primary factor for cancer risk. So the cobalt sulfate heptahydrate cancer slope factor was normalized to the content of cobalt from the specific NTP study. Now, there was another hitch here. Even though NTP throughout their entire document talks about cobalt sulfate heptahydrate, what they actually found they exposed their animals to was the hexahydrate, which I show in red there. It was 6 H2Os rather than 7. Now, the heptahydrate dehydrates to the hexahydrate at a temperature of 41.5 degrees centigrade, which I think is equivalent to about 107 degrees Fahrenheit. The NTP, even though they talk about the heptahydrate throughout their document, and in nature you would be exposed to most likely exposed to the heptahydrate, their particular particle generating system resulted in the animals being exposed to the hexahydrate. They only mentioned this in a few paragraphs in their document. And this was pointed out in the comments that we had used the heptahydrate rather than the hexahydrate to normalize the cobalt content anyway. The point is here we use the hexahydrate, the same form of the sulfate that cobalt sulfate that the animals were exposed to, in order to come up with a cancer slope factor. And that was 3.0 milligrams cobalt per kilogram day to the -1. Now, the last calculation we need to do, we're almost done here, is what's called an inhalation unit risk. This is simply taking the cancer slope factor and converting it to a form or to units of micrograms per cubic meter to the -1. So this equation is the IUR is equal to the cancer slope factor times the breathing rate over the body weight times the conversion factor. So human breathing rate we use is 20 cubic meters per day. Average body weight is 70 kilograms, and the conversion factor is 1,000. This results in a cobalt metal IUR of 7.8 times 10 to the -3 micrograms per cubic meter to the -1. For cobalt sulfate, that IUR is about 10-fold lower, 8.0 times 10 to the -4. So what do these numbers mean? Well, for the metal, lifetime exposure to 1 microgram per cubic meter results in 7.8 chances of cancer in 1,000 individuals exposed. This is equivalent to 7,800 chances of cancer in 1 million individuals exposed. For cobalt sulfate heptahydrate, lifetime exposure to 1 microgram per cubic meter results in 800 chances of cancer per 1 million individuals exposed. Like to entertain any more questions, or should we go on to comments and responses?
Yes. But first, are there any questions specifically on the presentation? Any other? Ahmad?
Very nice presentation. I just wanted to, oh, yeah, I just wanted to go over the cancer slope factor derivation, slide number 30.
Was that 30 or
30,
13?
30.
30.
Yeah.
Okay.
Oh, it's slide number 30, page 16. In my,
I think
oh yeah, this is the one. Yeah, here you have introduced this formula to account for interspecies differences, and you are indicating the body weight scaling, which can basically take into account the pharmacokinetic and pharmacodynamic differences between human and rodents. What I'm wondering is, not specific to cobalt, but in general for all inhalatory carcinogens, clearly there is a great deal of difference between the anatomy of respiratory tract in rodents versus humans. The nasal cavity in mouse and rats is highly complex and enables them to filter out the vast majority of the inhaled particles, whereas humans is much simpler. And I'm wondering, is it accounted for anyway in this calculation? These anatomical differences? Because clearly the effective dose is not the dose to which the animal is exposed. The deposition of particle is far lower than the amount of the cobalt that these animals are being exposed to.
Yeah, this is similar to Dr. Clement's earlier comment. And right now we don't have, eventually we might be able to work in something like the MPPD model and account for deposition. But right now we're just not at the technical point of being able to implement that. And, even, for example, US EPA isn't doing that right now either. So it's something that we might try to do in the future, but we're not there yet. And this, the interspecies scaling factor doesn't really account for that. It's more for PB and, pharmacokinetic, pharmacodynamic differences. It's not so much for deposited dose, taking an exposed dose to an absorbed dose.
Is there any data, leaving aside doing fancy modeling, but is there any data of like what fraction of the exposed dose actually gets absorbed for cobalt? Does anybody know?
No, there's no empirical data out there for that.
One thing we have observed from our own study is that we have to increase the amount of dose 100 times, sometimes even 1,000 times in mice in order to produce the effects that are present in humans when they're exposed to, let's say, 1/100th of the dose or 1,000th of the dose. So there is a clear difference between the dose, effective dose between humans and rodents.
And would you be talking about, is that PM, for example?
It could be, for example, particulate matter as a index for that.
Yeah, there's some things like my kind of seat of the pants perception of comparing sensitivity of rodents to humans. Like humans seem to be a lot more sensitive, for example, to diesel exhaust in rodents. You see a cancer response in humans that's much greater for the same concentration than you would see in rats and mice. There's some things where it's the reverse is true. So it's probably going to go on a chemical by chemical basis, and don't have any empirical data for cobalt where we can really tease that out.
In terms of the deposition, that's going to depend on particle size, of course. And I was going back, you were saying that they called it heptahydrate, but it was actually hexahydrate. And I didn't read the original paper, so I apologize for that. But how were they actually producing the material they were exposing the animals to? Was it at the higher temperatures that they were producing it? And do they, to say which is the right way to calculate that really would depend on whether they were weighing it before and it got converted in the air, so it's a different thing, but you wouldn't take that into account in the calculations. Just depends on when the weighing was done.
Well, I believe it was partly the way that they were actually generating the aerosol, and it was heating the material up enough that it essentially desiccated it. You drop that one water molecule.
But I guess if they weighed the material before they heated it up, that's the weight that they're thinking the dose is, then you actually still want to stay with the heptate in terms of calculating the cobalt equivalent value. Because that's from which it was weighed. Yeah.
They used methods to actually measure what the animals were exposed to in the chamber, and they started with cobalt sulfate hexahydrate in solution and then atomized it, blowing it out into the chamber. They didn't describe heating it, but it's certainly possible they did in the process.
Also, if they actually were having it aerosolized in a solution, so
From a solution, yeah.
Right. So we're not talking about the
It desiccates.
cobalt sulfate particles. We're talking about a solution that has a water droplet that has that in it too. So therefore, the particle size might be known if the aerosolization or the nebulizer was known.
The particle size is between 1 and 3 microns. That's what they described it.
All right, thank you. Let's take a break. 5-minute break, so we'll reassemble at 11:10, and then we'll go through the comments relatively quickly.
And the combined, it is higher.
It's not necessary.
Well, we used whatever gave us Yes, I think for, 7.8, that was for the cobalt metal, that was basically, sorry, nails, mice. So in mice, they only saw quite as strong. What I was trying to explain to Dr. Hammond. Okay, comments and responses. We got comments from Tox Strategies, Cobalt Institute, and the the Color Pigments Manufacturers Association. These are just going to be the main comments. There were some minor comments that I didn't include in the slides here, but they were all in our responses were to everything. To every comment, and you got that in the package that we sent out a month ago. So I'm only covering the main ones here. Okay, so I'll go on to the first comment. Tox Strategies asked to clarify that cobalt alloys, in addition to cobalt tungsten hard metals, should be excluded from the cobalt and cobalt compounds categories. In other words, not included in the cancer slope factors that we develop for cobalt compounds. OEA agrees that cobalt alloys should not be included in the cobalt cancer slope factor categories. And we do say this in the document, that cobalt alloys have different chemical and physical properties compared to the cobalt compounds, NTP studies in particular. Some alloys are quite carcinogenic, for example, cobalt tungsten hard metals, and they would require a different cancer potency factor than the ones we develop specifically for the cobalt compounds in metal. Other alloys, cobalt alloys, are insoluble in weak acids and likely present no cancer risk. So again, we did not include cobalt alloys, with the cancer slope factors we developed. Comment number 2. Water solubility is a poor surrogate for solubility of metals under physiological conditions. Well, we had 3 parts, or divided in 3 parts, our response here. Number 1, solubility appears to play a role in cobalt-induced lung cell genotoxicity and suggests soluble and insoluble forms of cobalt may have different cancer or carcinogenicity potentials. As I mentioned earlier, the insoluble forms, such as cobalt metal, appear to be quite more potent in producing cancer compared to the soluble forms of cobalt compounds. Point 2 here is categorization based on water solubility works well under insoluble, because insoluble cobalt metal and compounds appear to be largely internalized by cells as particles. And point 3, keeping the classification information simple based on water solubility, whether it's greater than or less than 100 milligrams per liter, is adequate in determining which cobalt IUR or cancer slope factor to use. Next slide, comment number 3. Comparison of cobalt sulfate heptahydrate cancer potency to that of cobalt metal should be based on 1, content of cobalt in cobalt sulfate heptahydrate, not the content of cobalt sulfate. And point 2 here was NTP actually found rodents were exposed to the hexahydrate, not the heptahydrate form of cobalt sulfate. So regarding the first point, we corrected the comparison of cobalt metal based on the content of cobalt sulfate heptahydrate. They're specifically referring to a paragraph or 2 that I wrote in the cancer hazard evaluation section, section 4, where I made a comparison between cobalt metal and cobalt sulfate. And it actually should have been specifically to the cobalt content in cobalt sulfate. So I corrected that. In part 2, already explained the problem with the NTP study. They actually exposed the animals to the hexahydrate, and this comment in particular, alerted us to that. We hadn't caught that because it was only mentioned in a paragraph or 2 document. But this only adjusted the cancer slope factor slightly. It went from 2.8 to 3.0 milligrams per kilogram data to -1. Comment number 4. This is commented mainly by Tox Strategies here. Suh et al. Converted the 2 forms of cobalt to human equivalent concentrations using the EPA RDDR method, which is the regionally deposited dose ratio, and found the carcinogenicity or potency to be similar. Now, this is a graph from Suh et al. And what Tox Strategies in particular is suggesting is that if you connect the 2 blue lines, you could form a single line through all of those blue points, resulting in one cancer slope factor that can be used for both cobalt sulfate heptahydrate and cobalt metal. Likewise, you can combine the 2 black lines there and come up with one slope. They didn't actually plug this information into the US EPA benchmark dose software. They're just saying, it looks like you can make one line out of the combined metal and sulfate data. The cobalt metal data is up in the upper right, and the cobalt sulfate heptahydrate data is in the lower left-hand side. It looks like it's possible, but we have to consider the fact that the metal is likely more potent or carcinogen than the cobalt sulfate heptahydrate. So if you draw a line specifically through the data in the top right-hand corner there, the mouse and rat data, you would get a steeper slope than drawing a line through just simply the hexahydrate data in the lower left. And that's that was our response here, is that we're going to be health protective and assume, just like what the genotoxicity and lung cell culture data tells us, that there's definitely a higher potential for cobalt metal to be more toxic, more potent in terms of carcinogenicity compared to the soluble cobalt compounds. So we would prefer to do slope factors individually for cobalt sulfate heptahydrate and cobalt metal. Comment number 5. OEHA did not use dosimetric adjustments appropriate for each tumor site, which is inconsistent with USA EPA guidance and ignores the importance of variable lung deposition by particle size and species. Our response is that because there is evidence of systemic distribution of inhaled cobalt resulting in systemic tumors, we use body weight scaling to convert to human equivalents. This is a method used by OEHA for extrapolating from rodents to humans for cancer potency derivations. Using this interspecies scaling factor is preferred by OEHA because it's assumed to account for not only pharmacokinetic differences, but pharmacodynamic considerations as well. In comment number 6, the latest version of BMDS, or benchmark dose software 3.1, now contains recommendations and warnings for model selection of the BMR. A BMR of 5% for lung tumors in male mice resulted in a questionable recommendation because the 5% response rate is not within the observable range. We did go over this earlier, but they went on to comment that the custom BMR method is recommended, which has been used previously by US EPA in 2011. In US EPA's method, the custom BMR is calculated as follows, and this is the equation they used to come up with a different benchmark or BMR value to use. This particular method, when applied to the mouse data resulted in BMR of 78%, which they say is within the observable range. Our response is that, as noted earlier, OEHA recommends using the exact formula when the BMR at 5% yields a BMD that is not within the observable range. The US EPA BMD version 3.1 software shows that a BMR of 15% is a viable recommendation in the model, and applying the exact formula results in a CSF of 4.57 is the same regardless of whether the BMR is 5% or 15%. Now, to go on with the comment number 6 here, in this graph we show what a using a BMR 15% looks like. BMR of 5% would be a little bit lower on the line, a little bit closer to that control group there in the bottom left. But you get up to 15%, and now you get what's called a viable recommendation rather than a questionable recommendation. Okay, and so Tox Strategies in their Suh et al. Paper recommended, using this so-called BMR custom method, which came out of a EPA document, using a BMR of 78%, which comes out of this so-called custom method equation. It shows a BMD and BMDL that is in between the low and mid-dose group, and we really don't think that's health protective. We're really interested in what's going on between the control and the low-dose group. So we don't think this method is appropriate. In addition, the custom BMR method, as suggested by Tox Strategies, came out of a 2011 document, as I noted earlier, but this was actually an external review draft document that had never been finalized. Comment number 7. OEA modeled pheochromocytomas in rats both independently and as part of a combined analysis. There is evidence that pheochromocytomas arise in inhalation studies where hypoxia is induced as a consequence of exposure to particulate-producing lung lesions, including tumors. Thus, it is unnecessary for pheochromocytomas to serve as the basis of any cancer slope factor or IUR, alone or in combination, when a more relevant site of contact tumor is present. Our response was in 2 parts here. Due to the lack of confidence by NTP and other researchers have for the cause of rat pheochromocytomas, as OEA has chosen a health protective approach by assuming that pheochromocytomas arise independently from the lung cancer and non-cancer effects. And point 2, a number of NTP carcinogenicity studies observed pheochromocytomas resulting from a carcinogenic chemical that was put in feed or administered by gavage, and there was no pulmonary effects found in these studies. Therefore, we cannot ignore the possibility that inhaled cobalt metal and cobalt compounds that are absorbed systemically and reach the adrenal glands could be a direct cause of pheochromocytoma. Comment number 8. Due to increasing morbidity of the F344 intact rat colony and the lack of historical control data, the occurrence of systemic tumors in the cobalt metal study in rats cannot be conclusively interpreted. In other words, they wanted this particular rat data thrown out. We respond by saying NTP did not express concern that the strain of rat used in the cobalt metal study would affect the carcinogenicity incidence Some non-cancer endpoints may be affected, but not the cancer endpoints. And point two here is that OEA ultimately derived a cancer potency factor for cobalt metal based on the lung tumor data in male mice. So we didn't even use this particular rat data. In comment number 9 by the Cobalt Institute, the combination of both cobalt compounds into one dose response curve results in a very good model fit. The indication that the model is able to predict exposure responses at relatively low exposures. A detailed report on benchmark dose modeling of the complete animal data set is appended to these comments. So what Cobalt Institute did is they actually ran a dose response or benchmark dose modeling using the combined cobalt metal and cobalt sulfate data and came up with one dose response curve for both the metal and the sulfate. Hence, it resulted in one cancer slope factor for both of these compounds combined. The resulting BMDL value was 0.12, and so we calculated the cancer slope factor from that, and that was a rodent cancer slope factor of 0.42 from their data. They chose a 90% confidence interval bound around the BMD. Typically, we would use a 95% confidence interval around the BMD, so that 0.42 cancer slope factor should be actually a little bit higher by our methodology. But in any case, compared to the cancer slope factors we came up separately for the metal and the sulfate, that number that the Cobalt Institute came up with using benchmark dose software isn't that much different than our cancer slope factor we came up for the sulfate, which was 0.74 milligrams per kilogram, data to -1. For cobalt metal, the slope factor was quite a bit higher, 4.57. Again, as outlined in our earlier response, the lung tumor incidence slopes for cobalt metal appear to be steeper than the lung tumor incidence slopes for cobalt sulfate heptahydrate in both rats and mice. And we chose to calculate cancer slope factors separately for the two forms of cobalt. Comment number 10. Cobalt compounds such as cobalt oxide and cobalt sulfide have negligible solubility of around 1 to 2% in biological fluids, namely artificial alveolar or lysosomal lung fluids. And they should not be grouped with cobalt metal powder for endpoint inhalation toxicity. So they would like these low solubility compounds thrown out and not included in the cancer slope factors. And our response is in two parts here. In lung cell cultures, you can see up to 50% solubility of cobalt oxide particles within cells. So using artificial alveolar or lysosomal lung fluids may not mimic what's going on in the cells very well. In addition, a number of in vitro studies in lung cells observed genotoxicity and cytotoxicity resulting from cobalt oxide exposure. Therefore, cobalt compounds of low solubility are grouped with cobalt metal. The final comment here that I have by the Color Pigments Manufacturers Association. It is inappropriate for OEA to categorize all compounds with solubilities lower than 100 milligrams per liter as essentially the same for inhalation risk assessment. Complex inorganic color pigments, particularly cobalt, aluminum, chrome, spinel, do not yield significant amounts of bioavailable cobalt. So they would like to have this particular compound thrown out or not included in the cancer slope factors we developed. Our response is that OEA agrees with that cobalt spinels should not be included in the cobalt cancer potency factors. And we now say this in the document. And the reason why is the calcining process at high temperatures used to form these spinels, it's an interdiffuse crystalline matrix structure, and the process has similarities to the alloying process. So as I noted earlier, we do not include cobalt alloys with these particular cancer slope factors that we developed. In addition, spinels have very low solubility, even in lysosomal fluid. So we're talking about pretty low levels of 0.089%. And the final point here is that IR concluded there is currently inadequate evidence for carcinogenicity of cobalt, aluminum, chromium spinels. So we do not include the spinels in our cancer slope. All right, that's the end.
Great. Thank you very much, Darren. So what I'd like to do now is start with our leads. I know we've already had quite an extensive discussion, which is great. We would like to try to finish by noon, so let's try not to repeat ourselves from the earlier discussion, but if we have items that are new, let's talk about those. Ahmad, would you like to start? Anything to add?
Well, one thing I just wanted to mention is that perhaps it was not covered in this part of your presentation. It was regarding the way that the genotoxicity and mutagenicity of cobalt was presented in this draft. And it appeared to me that it's not very balanced considering the existing data that shows lack of mutagenicity and genotoxicity of cobalt in mammalian cells as well as bacterial systems. And it's just sitting outside and looking in, it appeared to me as if it is kind of going out of its way to show the positive data. So perhaps a more balanced presentation of the current data that are available in the literature help to make it a fairer review.
I could do that. I concentrated on the data that NTP generated in terms of the Ames assay results. I figured that was the best data that we had available for that type of assay. And I only referred to, that there were other studies that were done in the past, but I could, add a few more of the more recent ones.
There is no question that the carcinogenicity is out of the question, but you don't need to demonstrate that it's mutagenic in order to be carcinogenic, because more and more papers are coming out showing a non-genotoxic mode of action for this chemical, particularly the pathways involving ROS and oxidative DNA damage, and even more recent papers show an epigenetic mechanism involved. So perhaps that would help the argument.
Thank you, Ahmad. Joe?
Yeah, I appreciate all the effort you, John, and you put into the document. It's very well written, well organized. I'm just going to skip over some of my comments. And I like the nice, concise summary of the animal carcinogenicity bioassays. That was great data. I think you're absolutely right, the differentiation between the metal and the insoluble compounds versus the soluble ones. I agree with you completely, and I don't agree with the reviewers that made the other comments, because that's exactly the way nickel goes, and chromium as well. There's a big difference between the insolubles being phagocytosed and having a greater carcinogenic effect compared to the solubles. And with nickel, soluble nickel, it just doesn't work in animals. It comes out in the urine because there's no biological receptor. A little bit of soluble nickel gets in on the iron transport carrier, but it's not enough to cause carcinogenesis. So I think on your responses to number 2 and number 4 and number 11, you're right on the money. I would not budge on that. I think you're absolutely right. Let's see what else. And I feel the pheochromocytoma data is a little shaky. I think I'd stick with lung alveolar benign and malignant tumors. I think you're much better off. The epidemiology you gathered together, it doesn't show very much. I think that's the way it is, and that's the way it will stay for quite a while. And your discussion of the genotoxicity was very interesting, I thought. That you get COMET assay increases in the percentage of the tail, so that was pretty clear some type of damage is going on in the oxygen radical damage, and then that you get altered base DNA products, which were typical of hydroxyl radical attack. That's very interesting, and I think that's probably important in the mechanism. I agree with Ahmed. For arsenic, nickel, and chromium, Max Costa's lab has shown that in addition to all the genotoxicity studies done, they're getting epigenetic effects, changes in methylation of histones and how that affects gene expression also. Many of these metals seem to have a bifurcated type of mechanism, 2 mechanisms going on at the same time. So it's a complicated mechanism, I'm sure. So I think it's an excellent document based on a thorough analysis of the carcinogenicity and genotoxicity of cobalt metal and insoluble cobalt salts, and on the carcinogenicity of the water-soluble cobalt compounds, normalized the cobalt content. So I thought the document was pretty good. And you have the other comments we made with regard to the slopes of the curves and all that stuff from the transcript. You can get our comments from there, like using a linearly square fit models and comparing it to them or something like that. I think the document's terrific. It's very strong.
Thank you, Joe. I'd like to open it up to the other panel members. Any additional comments?
This is Mike. Just following up on Dr. Hammond's comment earlier, you didn't have any hotspot actual environmental measurements. Are there, any data that could be added to the report to give us an idea of what the actual exposures are? Cobalt?
Near hotspots.
Yeah.
We didn't find any. If it had been out there, we would have included it in the document. So, I mean, we put everything in that we could find.
Do we know what are the hotspots in California for cobalt?
Aerospace, metal finishers, cement kilns, some other facilities that use extensive material combustion. But I would say that the 2 top of the list would be aerospace, metal finishers, and cement kilns.
I would have thought there might have been some sampling near cement kilns conducted. I don't know that. I just would have.
Well, it's the chicken and the egg problem. If they did sampling, they probably didn't include cobalt in the list of analytes because it's not a problem.
Other panel comments?
Well, I guess the other piece of data that you do have, though, are the emissions inventories, right? Where you could at least identify areas where there might be exposure.
Well, all we had was the regional sort of exposures over urban areas where it was clearly higher, considerably higher when you compare it to the rural or wilderness areas. That's the best we could find.
I mean, even in the absence of hotspot measurements, those upper bounds that you gave for some of the urban areas in Southern California are above 1 in a million risk based on your IUR.
Yeah, that was noted by one of the commenters.
Yeah. So clearly, near a hotspot, you're going to have an issue.
Yeah, I would actually recommend that you describe a little bit what you just said in the introduction, where the hotspots could be from industry. And TRI data does not report cobalt because it's not a problem.
Well, TRI data does report it, but you can't get like a hotspot concentration estimation out of it.
Yeah, no, that's not what I meant. What I meant is maybe you can describe the TRI facilities that are reporting on cobalt, so you have an idea of what industries those are.
Right. Well, we can do that with the ARB, with the hotspots inventory data. So we could make a mention of, what types of facilities are likely to produce cobalt emissions in California, and maybe an estimation, like a range of magnitude of how much they're putting out. So we could do that. We could add that to the document.
That would be very helpful. Thanks.
Yeah, I would agree with that because I was looking at your slide 2 quite a while ago. And, from the wilderness and rural areas up to the high amounts of mean air concentrations in the urban areas, that's 1,000 to 10,000 fold increase. I mean, that's huge. That's enormous. So I would certainly agree with the other 2 reviewers to discuss it a little bit.
Yeah, those higher concentrations you see in urban areas, it's largely from various combustion sources, as you might expect.
Why would I expect that there would be cobalt from combustion?
Just that there's some very small amounts, but there are metals, for example, in diesel fuel. When you combust diesel, it's going to release these metals. I mean, if there's any coal sources, combustion coal, you're going to get metals put into the air.
So you're saying that the predominant source of diffuse ambient air pollution, cobalt, is likely to be fossil fuel use.
Various fossil fuels, yeah, some more than others. If you'd like, I could probably go into that a little bit.
I mean, it's not
as to
in
why
there.
it's higher in urban areas.
It's not in there now, particularly, or
I'm sorry?
it's fairly obscure in the document that a substantive proportion of ambient low-level pollution as opposed to hotspot pollution is likely to be from fossil fuel combustion as an actual contaminant of fossil fuel, if that's what you're saying?
Well, that gets to be a little bit harder to make that exact connection because, for example, cement kilns, we can't really say if for sure. Nobody's actually done a study that we're aware of to check to see, is it the materials going into the cement kiln? Is it the combustion process itself? We just know that cement kilns, are one of the leading emitters of cobalt. Exactly what the pathway is for that happening, we don't have that information. There's other things like, for example, motor vehicle traffic. There's a certain amount of cobalt gets used in things like pistons and piston rings and such. That could be a contributor, but we're hypothesizing. We don't have, like, say, a US EPA document that's looking into this and says, yes, this is where, if you have urban air and you've got this much cobalt, where is it coming from? So we're kind of making educated hypotheses.
Other comments? Lisa?
Had a quick comment. When I went through the document, and I may have missed this, there wasn't much of a discussion on susceptible populations of kids. Right. And I realize you're limited in terms of the data to draw from. Was there any consideration of, for example, in your calculations of an increased respiratory rate in children and how that might in fact, it goes back to potentially underestimating.
Well, we don't so much consider that in the actual document that does the hazard identification and the dose response analysis. But once we develop a cancer unit risk, that'll go into the hotspots facility risk assessment software where we did, the panel approved the guidance manual back in 2015, and that includes both tailored breathing rates by age group and also the use of the age-specific factors. So infants and children are expected to have a higher cancer risk if they're exposed at young ages than adults. So that's taken in consideration, but at a later part of the risk assessment process.
Oh, I have a somewhat related question. If you take the unit risk factor and convert it to an equivalent concentration that would result in a 1 in a million risk, you get about 0.1 nanograms per cubic meter for cobalt metal and about 1 nanogram per cubic meter for soluble cobalt. So then the mean Southern California concentrations are above that. So it seems that entire Southern California is a hot spot for cobalt. And so what do you do in that case? If most of your population is being exposed at a level, is 1 in a million the level at which you start to worry about the risk, or am I not correct on that?
Well, for example, South Coast AQMD requires risk notification at 10 in a million. So, and I think risk reduction at 25 in a million.
Risk reduction at 25 in a million. Okay, so you're getting, some of these are going to be close to that if it's cobalt metal.
Would depend on where it was. If you had a cement kiln out in Victorville and there's, out in the middle of nowhere and there's nobody out there, it might not. But if they were in, say, City of Industry with the residential population, then yeah, it's going to be on a site-by-site basis.
Right. No, what I'm saying is that these mean air concentrations in urban Southern California, it's close. 25 in a million would be 2.5 nanograms per cubic meter of cobalt metal. So certainly some of these maximum levels, it seems like you're going to have a lot of hot spots, which would be interesting and hopefully something we can do something about.
Correct. Well, this will be interesting to see downstream as this number gets adopted as to what effect it's going to have on hotspots facility risk assessments.
I had one other comment, was about the cobalt tungsten carbide, which appears to be more carcinogenic. Is that something that is common in California, that we should be expecting emissions of that?
Yes, it's very common in California.
Oh, it is very common in California.
Ubiquitous, I would say, in terms of any place where there's a hard metal cutting blade used. That would include anywhere that has industrial level saw blades or dental labs that have tungsten cobalt drills, or any other number of places, which would be the one area that I wanted to ask you to be a little bit more clear in the executive summary, which in fact does not distinctly mention hard metal. It refers to alloys. In your presentation, you were clearer in your first slide, but in the executive summary, not clear that that's being talked about. And since later, suddenly in the document at a certain point, it says, not only this is more carcinogenic, but this was not covered in this document. I think it, you know, that's worthy of being clarified in the executive summary so that nobody will be surprised come to that. And because technically, tungsten carbide cobalt is not an alloy. In a metallurgic sense, it's in this other category of pseudo-alloys or whatever. It's not a true alloy, unlike the steel cobalt alloys. So if you use the word alloy, it wouldn't subsume tungsten carbide cobalt.
No, I didn't realize that they called it a pseudo-alloy.
Well, don't call it. I'm
I
using
haven't
that
seen
generically.
that term, yeah.
No, that's my made-up term.
Okay.
It's not an alloy at all. It's a something. They refer to it as a...
The process, as I understand it, they heat it just enough so that the
Sticks together.
dust particles stick together. Yeah, and when that
So-
happens, you get this different type of
Right.
process.
Conglomerate, right? I've never been clear what the technical term. It's often made through a sintering process, but anyway, that's too much detail. But it's not. It's actually not mentioned in the executive summary, where alloys are mentioned, but not this.
Okay, I'll fix that.
And it should also say that they won't be included here, even
Right.
though it's more carcinogenic. And I thought it was good that you at least alluded to the severe lung disease that substance causes. Actually, probably cobalt alone, without that, can probably cause giant cell pneumonitis as well. Again, I don't know if that's too much detail for you to go into, because those cases where that disease occurs with pure cobalt are, it's by far not as common.
I could mention that. I believe that type of lung disease caused by cobalt alone is also considerably less than fine tungsten. Cobalt.
Yeah, it's not
Yeah.
it's much rarer, and a lot of specialists don't realize and think it can only be caused by tungsten cobalt carbide. And cobalt also is one of the metals which potently can cause asthma in insensitized workers. Again, it's at your discretion if you want to. You have not talked much at all about the other serious health effects of cobalt. And I don't know if it's too much of a diversion to have one or two sentences where you talk about it, but cobalt is quite an interesting toxic metal, and its association in metal on metal hip disintegration and severe cardiac disease, as well as deafness. So it's ototoxic, it's cardiotoxic. It's an interesting substance. I don't know.
That's getting a little bit outside of what we're trying to.
I understand that,
this
but you
is a
do talk.
cancer
I
document,
think it is
and-
appropriate that you have the
Yeah.
sentence or two that tungsten carbide causes
yeah,
this
we can
other
do that.
disease. So if you wanted to say just cobalt has other non-carcinogenic, serious human, well-known human toxicities with one reference, it wouldn't be a terrible thing to do, but it's completely your editorial discretion. There's enough reviews, you could just cite one of the reviews or something.
Okay.
Because people who read the document, who know cobalt, will have that in their minds. This was such high-profile stuff, and I grant you, it's not. Some of these effects are by systemic absorption, and not at all through.
Thank you, Paul. Joe?
Well, I was on the NTP panel that dealt with cobalt tungsten carbide, and it's phagocytosed very well. And that undoubtedly contributes to its carcinogenicity, as a mechanism of uptake. So it was notable how well it was phagocytosed and how carcinogenic it was.
Is cobalt tungsten carbide on OEHA's radar for a cancer potency factor?
Not right now. I'm truthfully not up to speed on what if, for example, if there's an NTP study out there that we could use or not.
Any other comments from the panel? Yes, Stan.
Well, just for the record, when I met with the OER people yesterday, I found a few spots in the document that I thought weren't clear. And we talked about how they could rewrite them to clarify some things. There are no substantive changes. I just want, and they've got that. But, so I'd like to come back to my suggestion that the alternative analysis with the slope, the 15% and all that be dropped. I think you can leave in that the program said that there's concern about the extrapolation, but then you can say that the concern is that we're underestimating the risk. But I mean, the difference, as you pointed out, between the direct estimate and the alternative is trivial. And I think all you're doing is making it unnecessarily complicated. So I really think that ought to be deleted.
So you're saying the alternative treatment with the quote-unquote exact calculation should be deleted?
No, it's
No,
not
you-
really an exact calculation.
Right.
It's-
That's why I
it's-
put the quotes around it.
Yeah, that's what they called it, but it's not. And again, it relies on the beta 1 parameter estimate, which came out of the curve fitting program. So all of the problems we talked about are embedded in that. So I just think it's cleaner and more defendable. And in the end, it doesn't make much difference to just use the BMDL 0.05 that comes out of the program and just say, the program highlighted that there's a lot of uncertainty because the lowest positive dose is pretty high, and the consensus is that the uncertainty that's introduced means that we're almost certainly underestimating the risk, and it might be a substantial underestimate, but we don't know by how much, and just leave it at that. I just think it would be a lot cleaner, and then you don't have to get into an argument about why did you pick 15%, for example. And the truth is, well, it made the computer program happy, which we've all been critical of, and so I really think that should just be taken. I mean, it's always easy to hit the delete button, I'm not actually gonna add anything. So are people okay with that?
I think that's a reasonable approach.
So what Stan is asking is that essentially that we're going to take our animal cancer slope factor of 4.57 and adjust it down to 5% BMR, which only results in a reduction from 4.57 to 4.46.
Yeah.
And
Or
when
if you
we-
round
when you
it off,
round
they're
it to-
both about 4.5.
Right, when you round it to, in the end, round it to just one or two significant factors. Numbers.
Yeah, it's not
gonna
gonna-
be really hard, little or no difference.
Yeah, that's right, but you just avoid one thing for people to like me to criticize.
That sounds entirely doable.
Okay, well then, having said that, I'd like to move that we accept the report subject to the modifications the panel suggested, and then say that OEI can just give it to the chair to review, and then if the chair thinks it's okay, then it's done. If there are issues that the chair thinks need to come back to the committee, then we can have another meeting on it. But I didn't hear any hugely serious criticisms of the rest of it. I'd like to move that.
I'll second that.
Okay, all in favor? Do a
Aye.
raise of hands, and then I'll verbally. Okay, so it's unanimous in favor of the motion. So we will take care of it from here. Thank you, everyone. We're going to take a break for lunch now. Reed's going to bring in lunch, and Lisa has to go teach, so we bid her adieu. And I'd like to thank OEHA for a very nice document, and we will reassemble at 12:30.
Term is for. No, they have a metallurgic. There's a metallurgic term. But it's definitely not now. It's not ever seen a sinter inductor? Like metal powders or powders. Oh, you put them under great pressure.
So, yeah, I mean, I think it probably represents.
Above, not below. And then I just need to send you receipts.
Just that I haven't traveled times since I'm not saying I always give you guys max macros.
Well, we can't get max and you see you have to.
It is a full-time job.
Yeah.
Yeah, then you need the need the miles, or you take it from Google.
What I do is just whatever you say. Unless you had to take a different route.
No.
For traffic, I can justify.
Well, I guess we got our act together and finally got it done, huh? Me too. That's the problem.
You paid him like $70 million. Rather way to save money. Like $75 million a year. Well, all of us looked at this and we said, this is not going to work. Central shared services. Instead of having my person working for all my grants, you know, had to go into this plan and everybody, so, and all the HR and all the financial stuff. And I'll tell you, nobody. It was horrible. Back like that, just to. Back we said, every moment has to be well, it costs money to get that. We're still losing millions of dollars.
But was it coming down as a function of
Not really. I mean, they basically gave it up. They finally admitted it failed. You know, but meanwhile, let me tell you, I had 2 grants where HPV were linked. I couldn't do it for life in the last 3 years. I had no idea. My legal I would overseas. dollars. I have a few slush funds. I was sick. I was actually, I mean, not by 1,000. I don't, if I knew within 10, and usually I'd want to know within 1,000. I couldn't figure out within 10,000. You did? Oh, that's right. I remember seeing, how was that go? I was wondering about that. That's right next door. Well, we probably ran into each other. Oh, yeah. Oh, yes, 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 yes. Right. That's like I was, my family moved when I was 7. I actually went to high school till I was just there last that was fun. It was really the 70s under risen the living there now. I'm proud to hear that. It was really bad. I've always liked them. I mean, they have a fabulous yeah, it seems like USC is kind of had a rough time too. And they yeah, well, they have to go to the well, they had to. Well, they didn't have to put in skyboxes, et cetera, et cetera. And so anyhow, they appeared, it was on like urban studies that show all the different ways to like, and it turns out I'm the national expert on how to finance taking is at the hospital. They listened to exactly. Well, I always figured they could, the business could have used the figuring out the better way to do the finance of the school as a business model, class study, you know, and have students come up with different ways and stuff. And then exactly to go and pay this outside firm that totally messed them up. But you know, but then they do the stadium and they do that. They don't talk. was a little part of why Dirks came down. The final coup de grace was the sexual harassment scandals that were happening on campus. And then the law school did. Basically, they said. Right. The Indian part. And what happened is I mean, because he was making it. And then he went to the press and
Michael Crimson.
is totally the chancellor's taken that away immediately. Exactly. And to blame Tanzan is Is he? Yeah. Oh, good.
I think Joel is not offended.
But it was a friend or just something. Put him in church. Oh, yeah. Then she inherited. When I was at UMass, a bunch of my friends said they were so glad that we got rid of that they were able to finally get rid of this guy. You know, and so suddenly we were stuck with this, lemon. Of course. I mean, Oh, the higher ups want it, yes. Yeah. I could not figure that out for the life of me, but. What?
Listerine. And it's still. Who has a sterling?
It's considered the tops in the country. I mean, it's the tops, but sometimes it's hard because but I think we'll run into yeah, they don't talk about this. Well, I'm sure he didn't. I'm sure he didn't. But he wasn't trying to do it, was he? It was really him.
Yeah.
Oh, I thought it was the. Hired because he was. That's what I tried to tell her. The School of Public Health. And I said, if he probably don't fix it. I said, don't kill a goose that's laying the golden egg. And I said, if you put in that structure, right now I walk down the hall, I talk to the person, I have my person,
All right, everyone, welcome back. So our second major agenda item today is a review of the proposed changes to the chemical substances list in Appendix A of the AB 2588 Air Toxics Hotspots Emissions Inventory Criteria and Guidelines Regulation. Just a little background first. So under AB 2588, certain facilities are required to report their emissions of specified toxic chemicals. The implementing regulation, which is known as the Emission Inventory Criteria and Guidelines Regulation, was last updated in 2007, and California Air Resources Board is considering amending the regulation. So Dave Edwards, the Assistant Division Chief of the Air Resources Board's Air Quality Planning and Science Division, is going to provide us with an overview of the regulation and a summary of the changes being considered for the chemical list. So I turn it over to Dave.
All right, great. Thanks, Court, for the introduction. All right, so for my presentation today, I'm going to start with a general overview of the AB 2588 Hotspots program that briefly goes over some of the key points that we presented to you at the June 28th meeting. We'll then move into the main topic for today's discussion, which is your review of the list of chemicals that we are proposing to add to Appendix A of the Emissions Inventory Criteria and Guidelines document. I'll then provide a brief synopsis of the substance selection process, go over a number of questions that we would like you to consider and then go over a number of questions we would like you to consider for your review. Lastly, I'll walk you through through the proposed timeline, the opportunities for public comment on the proposed list of new substances, and the process we envision for documenting the results you review. All right. So just to start with a little bit of background, as you may recall, on June 28th of this year, CARB staff made a presentation to you in which we informed you about our plans to update the Emissions Inventory and Criteria Guidelines Regulation. In that presentation, we provided information about the revisions that we were considering as part of the regulatory update, and also discussed the statutory requirements that guide the compilation and updating of the Appendix A chemical list. We also made a request for your assistance in reviewing the list of proposed new substances. Next, I'd like to go over some of the key points that we previously discussed with you concerning the Air Toxics Hotspots program. As you may recall, the goals of the program are to collect air toxic pollutant emissions data and make it available to the public, identify facilities that may have localized impacts, assess the risks to public health, and notify nearby residents about significant risks, and reduce these risks to levels that are health protective. One of CARB's responsibilities under this program is to develop and maintain the Emission Inventory Criteria and Guidelines Regulation that provides direction to facilities on how to compile and report their air toxics emission data. A key piece of these guidelines is Appendix A, which provides a list of chemical substances that may pose chronic or acute health threats when present in air, and which must be reported as part of a facility's emission inventory. Under the regulation, facilities are required to report their emissions on a 4-year cycle. In Appendix A, the Emissions Inventory Guidelines, chemicals are grouped into 3 tables. Appendix A1 lists substances for which emissions must be quantified in a facility's emission inventory. These are substances with the potential to present adverse impacts to public health due to their toxicity and potential to be emitted to the air from operations at California facilities. Appendix A2, substances for which their production, use, or other presence must be reported. These are substances with recognized health effects, but for which the usage and potential to be emitted to the air in California are less certain. Information on the production and use of these substances helps CARB and OEHA staff better characterize their potential to become an air pollutant that could create exposure to the public. Then lastly, Appendix A3 lists substances that are required to be reported only if they are being manufactured in California by a facility subject to the program. An example of a substance that may be assigned to this table could be an oral pharmaceutical that would not be expected to have airborne emissions of concern at its point of use, but for which the manufacturing facility could have the potential to release the material during manufacturing and handling processes. For this next part of the presentation, we'll present us an overview of the selection process for the new substances, go over the documents that we did provide for your review, and also walk you through the questions we would like you to consider in your review. So in the June 28th presentation, we briefed you about the 6 source lists of chemicals that CARB staff must consult for compiling and updating Appendix A of the chemical list. These lists include California's Toxic Air Contaminant List, US EPA's Hazardous Air Pollutants List, the International Agency for Resource on Cancer, California's Prop 65 list, the list of the National Toxicology Program, which is an interagency program within the U.S. Department of Health and Human Services, the list of California Department of Public Health's Hazard Evaluation System and Information Service, and also the 2588 statute gives CARB specific authority to include additional chemicals that may present a chronic or acute threat to the public but have not been formally listed in the 6 sources mentioned earlier. CARB staff, working closely with OEHA and DPR, evaluated over 1,300 new substances using the following selection criteria. First, the recognized toxicity under one of the 6 mandated lists or under CARB's authority, and the substance can become airborne and be present in California. Our review resulted in 812 new substances being proposed for addition to Appendix A, with 639 substances being proposed for A1, 11 for A2, and 162 for A3. Also through this process, staff did identify 548 substances that were deemed as not meeting the selection criteria due to insufficient evidence for cancer or non-cancer health effects or not being likely to become airborne. After the June meeting, CARB provided 4 documents to facilitate your review of the proposed new substances. The first was a document intended to provide the necessary background and context to understand the organization of the tables and selection criteria for the proposed new chemical substances. The second document was a copy of the existing Appendix A list, which was intended to provide a reference of the types of substances already regulated under the program. This list contains substances in Appendices A1 to A3 of the current regulation, which was last fully revised in 1996 and only partially updated in 2007. The third document, which was provided in both Excel and PDF formats, was the master list of new proposed substances. The last document consisted of several subsets of the master list grouped into 8 different categories requested in our June meeting. The categories are carcinogens, developmental and reproductive toxicants, pesticides, metals, other organics, pharmaceuticals, neurotoxins, and other. The other category, yes. I was.
Okay. Well, so why don't you, I missed the earlier meeting, but why don't you have pulmonary toxicants and cardiovascular toxicants on the list?
Yeah, that is something additional we can consider. It's likely in the other category at this point.
This is Kathy. Actually, when I looked at, since he brought that up, when I was looking through the material, I found this way of laying it out confusing because partially it's outcomes and partially it's chemical categories. So it's kind of a funny mix, frankly.
Yeah, and there is some overlap between the lists.
Right.
So.
Well, yeah, so I would think there would have to be.
Yes.
So, yeah, in other words, going to Stan's comment, there are a lot more outcomes we care about than just those.
Yes. Yeah, and that's definitely understood. The list is pretty expansive, so yeah, there's a lot of ways to slice and dice it. All right, so to continue, the other category, which is the roughly 300 or so chemicals, does have other categories within it, such as endocrine disruptors, respiratory, eye, or skin irritants, sensitizing agents and asthma triggers, persistent and bioaccumulative toxics, and also chemicals that are being proposed as part of new or already existing chemical groups, such as isocyanates, polycyclic aromatic hydrocarbons, and PAH derivatives. So to kind of further go into the list a little bit of how um, the magnitude of these substances are broken down by the category, as I just mentioned, you could see sort of the breakout on the slide above. As I mentioned earlier, note that some of these categories may overlap. So, for example, a substance could be categorized as both a pesticide and a developmental and reproductive toxicant. All right, so at this point, I think it is important to provide some context for this review. The AB 2588 statute does not explicitly require the SRP to review new chemicals for consideration under the program. However, we do feel that this is an important step in our process because this list is an integral precursor to the work OEHA does, and then you ultimately review and approve. That said, this consultation is new territory for everyone involved. Therefore, we have prepared a number of questions that we hope will guide you in your review of the proposed new chemicals. First question is, and I'll go in more detail on the next couple slides about this as well. Are we missing any important air toxic chemicals from the proposed list? Are the functional group characterizations for emerging chemicals appropriate and adequate? Are there other functional groups to add? Are there any chemicals on the not proposed for inclusion list that should be included in one of the appendices? All right, so back to the first question. As mentioned earlier, the AB 2588 statute specifies 6 source lists for CARB to review in compiling the list of Appendix A chemicals, and also gives CARB explicit authority to include other chemicals of concern. Several environmental health experts have expressed concern to us that many new chemicals are put into commercial use only to be later found to pose significant public and environmental health threats. They pointed out that it can be decades before emerging chemicals can make it into one of the 6 lists cited by the statute. So they have urged CARB to take a more proactive approach and include emerging chemicals in the AB 2588 list. An example of a data source that we reviewed for emerging chemicals is the US EPA's Significant New Use Rules. In requesting this review, we are seeking your guidance on whether there are additional chemicals or chemical lists that we should consider adding to Appendix A. Our second question pertains to the use of functional groups as the basis for adding new substances to the list. In the past, chemicals were added to the list as individual substances or as part of narrowly defined groups. In the proposed new list, CARB staff have proposed 3 broad functional group categories that include poly and perfluorinated chemicals, derivatives and substituted versions of polycyclic aromatic hydrocarbons containing any halogen atom, such as chlorine, bromine, fluorine, or iodine, and any chemical containing the isocyanate functional group. We are proposing that any chemical containing these functional groups should be listed in Appendix A1 because we believe it can be reasonably expected that they would have important health impacts. We would like to get your opinion on this proposal and also on any additional broad functional group categories that you may want to recommend for inclusion in Appendix A. Our third question is whether any of the chemicals on the not proposed for inclusion list should be included in one of the Appendix A tables. In reviewing the candidate chemicals, staff considered many factors that could contribute to their potential for public health concern. For example, we looked at the chemical structure and other properties that can inform whether a substance can become airborne. We also looked at special considerations for heavier substances, such as how is the substance being used and whether it can become airborne as a result of its intended use or as a byproduct of a physical or chemical process. For example, a substance created as a byproduct of combustion could become airborne even if it is not volatile at room temperature. We would like to rely on your expert opinions to make recommendations on any chemicals currently not proposed for addition that should be placed in one of the Appendix A tables. Now we'll focus a little bit on next steps and the process that we're looking at. As mentioned earlier, this consultation is new territory for everyone involved, and the format in which the panel would convey the results of their review is not yet clearly defined. We would like to get written recommendations in which you either express your scientific scientific acceptance of the proposed new substances, or provide recommendations for additions or deletions to the proposed list, and also provide guidance on the appropriateness of using functional groups as the basis for listing groups of substances. In order to allow for adequate time for review of the proposed revisions and proper consideration of public comments, we are proposing a timeline that begins with today's panel discussion and which continues with a webinar on November 20th. We anticipate that at some point after the November 20th webinar, and if necessary, early next year at the February meeting, the panel might be ready to issue preliminary recommendations. Final recommendations would be issued in late 2020 or 2021 after we report back to the panel on the outcome of our board hearing on the regulation amendment. As for the rulemaking schedule for the emissions inventory criteria and guidelines amendment, our aim is to start the public workshops on the proposed updates in early 2020. We anticipate taking the rulemaking package for our board's consideration by late 2020, and we'll report back to you on any final changes to the proposed new chemical list after our board hearing. Public comments on the proposed Appendix A chemical list will be accepted as part of this review and the Guidelines Regulation Amendment process. The comment period for the SRP review has been extended until November 8th, 2019, and comments received by this deadline will be addressed at the November 20th webinar. Comments received after this comment period closes on November 8th will be addressed as part of the Guidelines Regulation Amendment public process. Comments on the proposed new Appendix A chemical list should be emailed to Gabe Ruiz, who's manager of the Toxics Inventory and Special Projects section, to my right, or to me at the email addresses shown on the screen. As I conclude my presentation, I would like to put our questions for you back on the screen to provide a starting point for the ensuing discussion. Thank you very much for your attention, and at this point, we'd be happy to answer any questions you may have for us.
Great. Thank you very much, Dave. First, one clarification and correction. The teleconference meeting we're going to have in November is November 22nd, not the 20th. So SRP members, put it in your brain and on your calendar. It's the 22nd, and it'll be in the morning. Jim's already sent out the email with the day and time, but it's not the 20th. Okay. Thank you very much, Dave, for that. I open it up to the panel. Comments? Joe.
Well, initially, just let me restrict my remarks to carcinogens. I teach this to the graduate students every year, and there is a million-fold variation in potency of carcinogens. So that we don't bankrupt the state, I think you should prioritize them in terms of those that already have cancer slope factors, move them up to the top. And for instance, dibenzoalpyrene is more than 100 times more active than benzoapyrene, which is already extremely active. So that kind of stuff you want to move up to the top if you can.
Great. Thank you. Yes.
Let me clarify on that. I mean, the purpose of this list is to require facilities to report their emissions of these substances, right? A WEHA will make the determination of what's the order in which substances will be tackled for whether it's a REL or cancer potency factor. So we would just want to make sure that things that make it onto this list are substances that we should be concerned about. And then a WEHA will do the prioritization of the order in which they get addressed.
Yes. Yeah.
A question that would help us inform our input for you. The earlier slide, which had the table of the new things on the list summarized by category, was one of your earlier slides. Yeah. So these are new, so these are not ones that are already toxic air contaminants, correct? Just want to make sure I got that part of it.
Correct. Yes.
Right.
These would be new proposed.
These are the new.
Yes.
it would if the old ones, the existing ones, have already been similarly categorized, or if they could be similarly categorized, it would be rather interesting to see proportionally where are you adding more, because this one, I suspect the reason there are very few metals on this list is because there are a great many metals that are already regulated, for example. But the neurotoxins, there may be relatively fewer proportionally that are already regulated. So it would help you see what the impact of this list is in terms of how would it be changing the mix. Although I will say that I absolutely agree with what was said earlier, is it's rather confusing, those of us who like Venn diagrams in our heads. We see these groups and it's sort of mind-boggling because it's, apples and oranges, and so it is hard to grasp some of it, right? I mean, most of the metals are neurotoxins, so I guess they're in both categories, that kind of thing. So just for what it's worth, some of this is based on human health effects, and some of it's based on substance category. I mean, you can imagine if you had something up there that was chlorinated hydrocarbon as a category, how confusing it would be. So I'm not, I'm not convinced that this is necessarily, this many groups, is helpful. I understand why you want developmental and reproductive toxicants, because that has certain regulatory driving effects, as does the carcinogens. But once you get to other things, I'm not entirely convinced. But anyway, I don't want to overplay that. But I would say it would be nice to see side by side, because it's, if we look at a table like this, we have to bear in mind constantly, well, what's already listed. So it's not here because it's not listed, not because it's not here because it's already listed. I'm sorry, not because you forgot about it or something, right?
Yeah, so we can definitely provide that to you, the breakout of the existing list, and then sort of overlay that with this proposed list, so you can sort of see side by side. For example, metals, the number really is much larger based on the existing list as well. And then I'll also turn it over to Beth to kind of maybe give a little bit more detail. I'm sure she can talk a little bit about how that looks currently. Just
Yes, thanks. You're absolutely right. There are almost all of the typical metals are on the list already. In fact, we have cobalt, for example, as a single entry so far, but we will be expanding it in this round to more closely match the health values in the way they're structured that it was just approved this morning. But the other thing is just the categorization is not something that we routinely do. It was actually kind of an outcome of the last meeting that we had with you folks in June. There was interest in saying we had it so that you could easily find which source list it came from, but there was interest in at least several of these were named by folks that said, well, if I were going to kind of focus on my area of expertise on the list, I'd like it broken out by these. So we tried to just kind of follow the suggestions that were made. And yes, there are many other types of health effects that could have been broken out, but I think these were the ones that we heard from the panelists that were maybe in areas of specific interest to someone, so we tried to do that. But yes, as Dave said, we could certainly follow that same pattern and apply it to some of the existing list chemicals as well.
Kathy, as a chemist, I have to say, don't we want to have other organics on their list? I mean, this is an area that we need to. Now, I'm sure that organics are represented in the outcomes, but there might be organic chemicals that are suspect. So just kind of in a sense of completeness. So then at least that way we've kind of at least accounted for the chemicals, the sources. And then from the other side there are these other health outcomes. I mean, I think the point really isn't even the categorization it's really how they came to your attention. So of course we have these various carcinogen lists, and so that's how they come to be there as carcinogens. But they're either inorganic or organic, right? And similarly, we now have Prop 65, so that also gives us the developmental and reproductive toxicants. So those are the kinds of things. So we should recognize that. But meanwhile, it certainly should be true if we knew we knew the pulmonary outcome led us to think of compounds. I think it would be good to think of the general outcomes we think of, and as another way to try to be collecting. In terms of the sources of data, just in terms of making sure we have a complete list of what's known. Another simple one, and maybe everything is already covered, but just to say, have you looked at the ACGIH threshold limit values? I would at least want to make sure that we've included them all. They're like 650 or so of those, but it's just a list of, if they've identified it, we probably want to include it.
Well, so I wasn't at the earlier meetings I mentioned, and when I tried to look this over, I was like totally overwhelmed. But one thing you might want to do, because the master list is in an Excel spreadsheet, and you might want to have us add a couple columns, like one is outcome, one is chemical class, and one is source of where you got it. And then if you have that in your master list, then you could generate the 3 tables, one where you stratified on each of those things, and then the person, depending if you're like a biologically oriented person or a chemist, then you just look at the different lists. So that might help make it a little less scary.
Yeah, I'm just wondering about how practical it is to require reporting of some of these chemicals or substances that have been identified in Appendix A1. For example, environmental tobacco smoke or secondhand smoke. This is a complex mixture of several thousand chemicals containing toxicants and carcinogens. So each one has a different type of effect. So in these cases, are you going to measure a prototype or a representative compound from this whole complex to use it as an index? It's kind of confusing to me how that is going to be done. And the second point is that, well, by definition, every smoker can be a source of ETS or secondhand smoke. What are you going to narrow it down to establishment where smoking is allowed, for example, casino, or it's kind of confusing?
Okay, let me provide a little context. So this list is a part of the Air Toxic Hotspots program, AB 2588, and the program is focused on facilities, industrial facilities and commercial type facilities that are, the first step is to determine whether they are subject to that program at all. So there is a set of applicability criteria that are applied to that facility. And so generally speaking, we're talking about emissions from large industrial type sources, some smaller things. You can have smaller gas stations, auto body shops can also be sources without being large industrial type of applications. But the first step is determining that they are in fact subject to the Hotspots program. And then we also have exemptions built into the emission inventory regulation that this is a part of. And those exemptions are for like personal use by their employees of products, for example. So generally speaking, that the smoking that their employees might do is not part of what was intended to be covered by the statute. So the statute is pretty clear. It starts with large facilities that emit a lot of criteria pollutants. It steps its way down from a 25-ton facility to a 10-ton facility. And then it asked ARB to identify other classes of smaller facilities that should be a part of this program. So that's where we identified things like gasoline stations and auto body shops and dry cleaners and small chrome platers, things like that. But that is the first step. They have to actually be a facility subject to the program before they would even address this. So as it turns out, though, the main reason why you'd ever have a situation with, say, environmental tobacco smoke or tobacco smoke at all, we did recognize there are a few facilities that actually do testing and actually have smoking machines. So in a case like that, they might actually have to report these emissions. But by and large, most of the other situations would probably be covered by one of these personal use type exemptions and would not be something that the facility would be trying to quantify.
What would they report? What would be the unit of measure in this case?
I don't know that one has come up yet for sure. I don't know that one of these facilities that we had sort of heard about has actually come subject to the program. It would be in pounds, basically, pounds of that substance. It would not necessarily then be speciated. We could do that as another step. We could try to break it out using existing literature. But at this point, if they would just report the pounds of that substance, they would have met their reporting requirement, and then we would think about what we needed to do or what we would like to do with that data in terms of a further breakdown into components.
Just going down your list, I noticed that you have several of the carbonyl type compounds that are currently very popular flavors for vaping. Benzaldehyde, diacetyl. And I would suggest that you might want to bundle some of the, those up as you start to consider whether you want to look at potential risks from these things. That may be another way to categorize. So cinnamaldehyde, vanillin, benzaldehyde, diacetyl. I saw a couple of others. You've already earmarked them. But maybe if you look at them as a group, there may be a large aggregate.
Do panel members have any answers to Dave's first question? Are they missing any important toxic chemicals from the proposed list? Are there chemicals that people, maybe some of your favorite toxicants, you checked, you noticed they're not on the list? Anything in category 1?
Well, one of the problems is kind of what I was alluding to, which is we'd have to have at our fingertips what's already listed.
Well, so Dave did send.
No, I understand, but it's not a, I mean, I focused on this list, not on the list of, what is it, 600 or how many you have currently listed?
Right.
Right?
Yeah.
So that's one problem, but so it may not be something that efficiently can be done sitting here in front of you. What is missing, but I think you've heard a couple of good suggestions. Kathy said, look at the ACGIH list and just make sure that there's nothing missing from there. Look at the NIOSH handbook of chemicals. These are workplace ones, but still gives you a sense. Most ACGIH is actually more comprehensive than the NIOSH list, but I doubt there's anything on the NIOSH list that's missing from the ACGIH, but I can't say that for sure. You might also look, would be a useful table to you that's in the Olson Toxicology Handbook. Kent Olson has a very large table of toxic materials. Now, many of those are not airborne. It includes, other things that would be irrelevant, but it's the industrial chemicals there would be a good place for you to look and make sure that you, for example, got, well, a technical question, since you're considering, and this addresses one of your other questions, you're going to take a sort of group approach to isocyanate variants. So you're not going to necessarily have to list every one of them individually. Is that the idea there?
Yeah, that's the idea there.
Yeah, I think if you want my feedback, that's a clever idea. You might also consider the parallel reactive chemicals that are in epoxy mixes, which are called, what's the best way of summarizing those? In the epoxies, but there are a bunch of different.
Like the resin monomers, is that what you're getting at, or?
Well, it's the ones that react with them. Acetyls or something, I don't know. Yeah. those are a couple of examples of.
I mean, I totally agree with the concept there. But, the epoxide, the various epoxide and isocyanate compounds, which by the fact that they're reactive in terms of chemically for the purposes of an industrial purpose, they're also very reactive with human tissue.
So, for example, this morning, we had this. I noticed you put a bunch of cobalt compounds, even though cobalt is already listed as just cobalt metal, right? That's correct. So, would it save time? I mean, couldn't you take the same approach then with metals that have various salts and various organic things, that you didn't have to list 5 different cobalt subspecies?
I think you need to be careful with that because as we saw in cobalt, there was a huge difference in the toxicity.
Well, they could
and certainly
say,
nickel that's true of as well.
They could say soluble cobalts and salt. I mean, I'm just saying because you're going to miss some, right? There are going to be other ones that so you're either going to have to clutter up your list with lots and lots, or if there's shorthand. But anyway, that wasn't what I was about to say. What I was going to say is this morning at our discussion, it came out that tungsten cobalt,
Yes.
tungsten carbide cobalt, or aka hard metal, which is more carcinogenic than cobalt, unless that's already listed as a TAC, which I think it isn't.
We heard that, and we will be considering
not on
adding
this
that.
list.
It's
That's
not
an
there yet.
example.
We heard it this morning.
Okay.
May I comment just a little bit on that? So we're walking kind of a balance here between saying if we know about specific compounds that are in commerce now, it is sometimes an advantage to list them explicitly, even if it means kind of expanding under a group. Because if we can include their chemical abstracts registry number, their CAS number, that facilitates an industrial source who might be looking through their material safety data sheets, realizing that, yes, that is a listed chemical. And if we don't do that, we run the risk that someone who's maybe, a technician at that facility doesn't have the chemistry background, doesn't realize that this thing that they see on the MSDS that has a slightly different name really is a part of that group. So what we have been, this balance that we've tried to strike in the past has been that when we are aware of fairly commonly used explicit ones, we would try to put them on the list and include that CAS number because it makes it easier. We provide that list electronically. People can go through, an industrial facility can go through that list electronically if they would like to. But then the balance is that means that if something is emerging, we might not have it yet, and we'd have to go through a regulatory process. So that's the purpose of these 3 functional groups. We are saying that probably anything that contains those chemical functional groups, there's a reasonable probability that they would be having human toxicity concerns. And so we feel that that whole group could be considered as a new class. And then it's up to the facility to tell us a little bit more about what those chemicals are, rather than us having to already have figured out every single one. Does that
Sounds
answer your
great.
question?
This is more for my edification, but was looking at the list of not proposed, and I noted that you had wood dust listed, and it's indicated wood dust is a IARC-1 carcinogen, and it says should just report particulates. And I think that may be an oversimplification because if I remember right, not all wood dust is a carcinogen, but some of that which is not a carcinogen is a very strong allergen and is certainly related to occupational asthma in the woodworking industry. So I think that might be something that could be looked at with a little more specificity.
We've had similar discussions with our colleagues at OEHA and tried to grapple with that same kind of question of where would we go with this in terms of would a health value ever be adopted for a thing called wood dust. So it's a challenge, and any guidance you have on that would be definitely appreciated.
Yeah, the ACGIH TLV committee went into this in great detail and might be able to put you in contact with those folks.
Great, thank you.
I just want to make you aware that there is a big push right now to generate exposome data. And just in September, there was actually a publication in Environmental Health Perspectives by Barupal and Feen, Oliver Feen from, I think, UC Davis, on all of the chemicals that they were able to cross-link between different databases, including PubMed articles, and that might actually be a great resource to just check against. Because if it ends up in the blood, they look at the blood exposome, we know that people are exposed, right? Maybe it's not a health effect, but they are linking all sorts of databases, and you could at least use it as a tool.
Great, thank you.
For carcinogens, I would certainly recommend taking all the IR class 1 carcinogens, which are known human carcinogens, and the class 2, which are probable human, 2A, which are human, probable human carcinogens. And a lot of these have been picked up on the Proposition 65 list. The WEHA knows all about this already, the CI's carcinogen identification.
Thank you. Yes, we've tried to make sure that all the class 1s and 2As are somewhere on the list. In some cases, they didn't end up on Appendix A1 to be quantified because they may not have met that second criteria of whether they're likely to become airborne. Some of them, for example, are oral pharmaceuticals. And so that's where we tried to put them into some place like Appendix A3, where if you are a manufacturing facility, your handling as you're making it might result in some fugitive emissions. So a manufacturer of that pharmaceutical could be subject. But if you are just using that pharmaceutical at the point of end use and it's a pill or something like that, it's not, or an injectable, there's even some of those in the IR group ones, we wouldn't necessarily want that on the Appendix A1 for an industrial facility to try to quantify.
Kathy, I'm going to propose, or I'll ask the question first, but to what degree does ARB, stepping back, actually do any sampling to do any kind of validation of the emissions data that they receive from the facilities? And my guess is probably not very much.
So as a part of
I have a follow-up to that.
Okay. As a part of the emission inventory guidelines, of which Appendix A is one of the appendices, there is another appendix, Appendix D as in dog, that is a list of source types for which we are actually requiring source testing, airborne source testing to be done.
By the company?
By the company.
And where? Where's the testing? Is stack testing or
yes,
fence
usually
line? Or?
It's usually a stack type of test. Yeah, so for example, there would be the catalytic cracker at a refinery is subject to a source test. Because we don't think there's really any other way to get reliable quantitative data. So at the beginning of the Hotspots program, way back in the late 80s, those tests were conducted, and then ARB collected that data and developed emission factors based on that actual source testing. So that is now a pool of resources that other facilities might be able to use if they're similar enough. But yes, in some cases, we actually said source testing is probably the only reliable method to quantify some of these.
So I guess I think it's important as we go forward, I mean, just making longer lists of chemicals. I mean, first of all, I do want to acknowledge that this is a lot of work, and I'm appreciative that you're doing it. Let me be clear. But I think we also need to think about how that would be used. And so making sure, rethinking again, maybe it's time to retest with all the various air pollution devices. It's maybe times to retest because they're new chemicals that we're talking about, which may be bringing in new facilities. And maybe at a certain level, X percent, 3% even, something like that, some percent, that ARB does some testing to validate what the companies have done, and maybe some also community level testing to see what's actually making it into. I think you're right. Stack testing tells you something about emissions, but also then going out and seeing what makes it to the fence line or to the community. But I think that we need to take a more holistic view of this whole process.
Just one thing to add on that, the audit capabilities. I'm not sure how much it exists in the hotspots program, but our new reporting regulation, I think I talked to you guys maybe 6 months ago on that, our criterion toxics reporting regulation to get annual data on this as opposed to the every 4 year, which is limited in the hotspots program. There is a sort of audit verification component where we could go in, where we do at least have the authority that was in the health and safety code to go and evaluate whether the criterion toxics data that was submitted by a facility was accurate. So that capability does exist. We haven't explored that a lot yet. I mean, we're still working on just trying to get applicability, like who has to report in. But,
I mean,
but that it
you have that authority now, you're saying, or you haven't explored
just
whether
came
to
in
get?
like 2 years ago.
You just got, so you haven't actually exercised that?
Correct. Yeah.
Yeah, I think making this part of the planning would be an important piece, that's all. But that sounds like it is partly.
Any other comments related to Dave's first question? Any missing important air toxics? Yes, Mike.
You may have done this, but I'm wondering if you've cross-referenced the AB 617 locations and the emissions inventories that were used to help select the cities that are involved or the communities that are involved. And that may, if there was any of those that you're missing on your list, that would be have. Also, it might be a strategy for which ones do you want to look at first.
Yes, I think to the extent that most of those inventories were relying on the 2588 data from before, we have done that. And then I think one of the comments that came up last time was a great suggestion that we ask if there were anything else in those communities that we did not yet have. And we went through that process, and we did identify a couple of extra pesticides based on that review.
Yes, Joe.
And I was thinking on the carcinogen list, there could be certain chemicals that might be starred as of particular importance, even though they're already category 1. I'm thinking of 2378 tetrachloro dioxin, because the data from Seveso, Italy showed that it raised the cancer rates in almost every organ in the body in Italy, and the people who were exposed to it. And arsenic, which is like carcinogenic in 5 or 6 different organs. So things like that, which are multi-system carcinogens.
But Joe, those are already listed. I mean, those are not.
Yeah,
those
I said
wouldn't be
they're listed as category 1.
No, but I mean, they're already listed. They're not here
okay,
because
good.
they're already.
Good.
They're already.
Good.
I won't stake my life on it, but I'm.
Yes, those
very
have been in
sure.
the program for quite some time.
Right.
Yes, that's
so
correct.
it's a little bit like, Claude Rains in Casablanca rounding up the usual suspects. I think what they're asking is that, if we think outside the box, what is it that we're not thinking of? I think, is that correct?
Yeah, I think that gets to that functional group category. It also gets to the, like, for example, we mentioned this significant new use list that EPA puts out. Just because, as you sort of saw just from the background, this regulation has been really updated twice in roughly 25 years. So the opportunities that we do get to go into this are far between. So right now we do have an opportunity to kind of go in and try to at least be proactive in how we're doing everything as opposed to reactive, which is sort of looking at where the potential for development lies and what sorts of chemicals may be coming out, or functional group relevances may be coming out in the future as well.
So I second Paul's point about it's hard to figure out if a toxicant you're interested in is already on the other list, but you go into the PDF, you do Control F, you write it in and you see if it's there. So you caught all the ones that I could think of initially. They were either on the original list or on the new list. But I encourage other panel members, if you have some favorite toxicants, just check. See if they're on the old list, see if they're on the new list, and if not, let's discuss it at our November 22nd meeting. I was trying to think of what might emerging contaminants in California look like. So I was trying to think of emerging industries. And one of the ideas that occurred to me, may sound crazy, was cannabis. Right, a lot of cannabis cultivation in California now, a lot of cannabis processing. So I'm wondering, I know there are complaints about odors from cannabis operations. And so I'm wondering if there are actually cannabis-specific toxicants that we haven't been thinking about that might actually be important. So I would encourage you to see if there's any literature on that, and perhaps there are some compounds. Now, I know that in your do not include list, you had some things that were excluded because they were botanicals or natural. So it makes me wonder is if there was a cannabis air toxicant, would it be listed, or is it natural?
I don't think that our exclusion of a botanical is an automatic. It's
okay.
more that we looked at them and thought about how could they become airborne? Was that very likely in the way that they're used and things like that? And you're right, with cannabis being more of something that is vaporized or combusted, might be different.
Yeah, and I wasn't thinking of cannabis use, but more the processing to the point where it gets to the consumer. So, some of these farms are quite large, and I know that there are a lot of neighbor complaints in some cases. And so there may be some real issues there.
John Boudreau. I think, one question would, for example, an indoor grow house or greenhouse that's growing cannabis, is that an ag use? And ag uses are generally not covered under the hotspots program.
Right, but that would be the application of a chemical to the crop, right? I'm wondering if the crop emits something itself.
No, we're talking about, there are complaints that do come from indoor greenhouses or indoor growing areas that is pungent.
Yeah.
So, and the plants are emitting volatile chemicals, but, the question is that still, that's an agricultural production area. So is that covered under hotspots?
But just carrying it one step further, we had an extensive SRP review of secondhand smoke, and our findings led to its determination as a toxic air contaminant. So I suppose secondhand marijuana smoke might be an exposure that at some point could be considered. And another, no, go ahead.
That could potentially be so, but what we're really talking about here is the actual growing facilities.
No, I understand, but it triggered me thinking that one thing that's not on this list, because in secondhand cigarette smoke shouldn't be on this list because it's already been considered, right? So, but we've never considered secondhand cannabis smoke. So that's one thing. Another thing, thinking back to previous discussions that this committee has had, we had a very, very involved review of diesel exhaust. But my memory is that what we designated was diesel exhaust particulate, and that we never did designate diesel exhaust gaseous material.
But it's on the list now. Yeah,
So
I was going through the list, so I was surprised to see that, and pleased.
So that's
pleased to
good-
see that.
So the system worked, or whatever that's an example of something that slipped by. So if you've caught that, however it was that you caught that, good thing.
No, that was good work. Trying just another thing. Has anyone ever compiled a list, thinking of these big spreadsheets that Stan's been talking about, a list of the chemicals, how many facilities in California respond and say they have emissions, and that actually might be some really interesting things to start bringing those data together and looking at what we have and looking at it. Has that been done, or if not, maybe we could put that on the agenda.
That is one of the things that is an outcome of the AB 2588 process, is that these facilities finish their reporting. It's reviewed by the district, and then it's forwarded to CARB, and it resides in a database that we have here. So for all of the facilities that have been subject to the hotspots program, we do have what they've reported as their emissions. In fact, I looked up after I heard your discussion on cobalt. I was looking to see how many reported facilities. We have about 200 facilities that have reported just generically cobalt. We don't have the breakdown of the soluble and insoluble yet, of course, but we do have some.
And is that publicly available so people can do
Yes.
that?
Yes, it is.
Oh, okay, great. Maybe you can later send that around. That would be great because that'd be a great MPH project. Just to actually look. Has anyone actually looked at that as a totality and kind of? Have you been able to do that?
Yes, we get
Oh,
lots
good.
of data requests from researchers to look at that database.
No, but I'm wondering, has anyone compiled that to look at, okay, what do we know now? And has anyone really taken a systematic view of some of that?
We've
that we
done
know?
a number of analyses. We also have a mapping tool that helps people see on a map
okay.
where facilities are. You can ask for it by a specific
So like where
chemical.
are all the cobalt places and they'd pop up?
I don't know if we have cobalt on the map quite yet.
Not,
but
yeah, not on our map, but if you did a data request,
Data
we would
request
give you a
we get
list
to.
of the 200 facilities by county, zip code, address, and emissions.
And how the emissions are. Great.
Well, so if I could just go back to, and this may be more a question for lawyers and scientists, but if you've got a marijuana grow out in a field somewhere, that's agricultural. But if you're in a city and you've got an industrial greenhouse facility that's, then emitting stuff into the air outside the building, I mean, is that considered agriculture, or is that now become an industrial thing which would be regulated by ARB in terms of the emissions that make it out of the building? Because that Court is right. I mean, people are complaining about that, and if you can smell it, it's probably not a good thing.
Yeah, I think that is a discussion that we probably do need to have internally with our lawyers in the room to talk about sort of what is the extent of scope and authority that 2588 gives us to get into that category specifically. I do agree with you that there is some distinction between a crop growing in a field and a crop growing in an industrial building, and how the permitting structure works, what the classification is within that district as to how they classify that type of activity, because especially if it's indoors, it's a lot of backup, it's a lot of generators, it's a lot of more industrial type sources that might be being used. I think one other piece to kind of maybe add an extension on to think about potentially is also the processing side, because outside of the ag use side, then there's the actual processing of the plant, and that could have some also implications as well. So I think that is, I would strongly say is in the hotspots program. The growing piece is, I think, a gray area.
One
So,
of my students just did an ergonomics project on the ergonomic problems. And there are a lot, as it turns out, in cannabis industry. But looking at the pictures that he had showing that made me realize this was an industrial process as well.
so coming back to functional groups and categories, how are you dealing with the myriad of fluorinated carbons, being every different combination, they all have, all the freons. How have you dealt with that? Freon 123, Freon 124, Freon,
We have, I think it's a handful of the chlorofluorocarbons right now on the list, just a limited number, because those are the ones that had exhibited enough toxicity to be on one of those 6 source lists that Dave mentioned during the slide presentation. The others have not emerged as on the radar of these organizations, international, national, and local, that look at toxicity, health effect type of things. So those have not, we don't have a lot of the freons on the list. We just have a handful on the toxic list. They're handled in other programs here at ARB, of course,
Right.
but as far as the toxics program, there's only a handful that made it. Now, that's not counting these per and polyfluoroalkyl substances that are analogs to like PFOA and PFOS. Those we're trying to capture in 2 ways. We'll have a long list. I think we have something like 70 of them. let's see, how many did we have of those? Yeah, about 74 individual ones that we've been able to identify from known literature. But then we're also creating a functional group to try to get ahead of the emerging ones.
Yeah.
But are you asking specifically about just like the Freon refrigerant type ones?
Both, I think.
Okay.
And
Yeah,
then it gets a little bit more complicated because in addition to the sort of classic long chain polymers, there are also these fairly short but not monomer polyfluorinated materials that are used as water repellent coatings and have had a lot of human health effects. So it's complicated chemistry, but it's also complicated to capture them, I think, because they keep switching around and
yes.
they're not. And that's a good candidate for a functional group approach, I would say.
While we're on that topic, do other panel members have thoughts about other functional groups that should be considered? I think the approach is great. That was one of your questions. Is this a good approach? I think it's great because, right, otherwise it's whack-a-mole all the time. You add another CH2 group and it's a different compound. But if you've got the entire class, then you capture that. So are there other functional groups that panel members can think of that should be included?
Well, methylating agents are not great things in general. But I don't, beyond that, I don't have a very specific.
Aldehydes. We certainly know a lot of them I'm sure, are already on the list. And that's actually one of the big things in the diesel exhaust, but might add that. And I think for some of these groups, like aldehydes, sometimes you can have reactions that kind of capture a class as opposed to just doing individual compounds. You just get a chemical reaction for the functional group and get a total without necessarily having to identify them all.
And also, as a group, on your metals that you've added, I haven't gone through here with an eye towards it, but rare earth metals, have you considered them? I doubt they're already on cerium, lanthanum. Also, in terms of the metals that are in catalytic converters, that there's been some issues about, like ruthenium and platinum and palladium. You have to double check, but I'd be surprised if they were already.
Most of those are not yet on the list.
But maybe they're not on the old list right now.
Not on the old list. Not on the old list either. Questions? Thank you.
To clarify too, I saw that you had a bunch of beryllium compounds on the new list. Is that because the old only just had beryllium generically, and this was an example of you trying to get specific CAS-associated entities?
That's right. We had some, but we're adding additional ones.
Okay.
And we put a little E in the column on the spreadsheet so that you can tell what we tried to do is bring the group together so that you could see it in context.
Right.
But the E are existing ones, and then without
Gotcha,
the E
gotcha.
are the ones
Yeah.
that we're adding additionally.
I have to say this is kind of amazing and overwhelming to me, what you're trying to do here. But I think it's really great to step back and not just be in our old world all the time. But just another list I thought of is maybe the EU band, looking at the EU REACH chemicals that achieve a certain status there. And I'm not sure how I would divide that, but at least look at that as a source to think about.
We did pick up some from that, but I'm not sure it's been a comprehensive look at that, systematic.
Yeah, I think at this point, I would add that voluntarily, to your list of, to always be paying attention to.
I had one comment on functional groups. So you've got halogenated PAHs, but I'm wondering about other classes of PAHs, nitro PAHs, polycyclic aromatic quinones. Certainly, they are toxic. And I don't know if you just hadn't considered it. I mean, some of them are secondary, right, formed in the atmosphere, but I suspect that there are emissions, at least, of some of those different types of compounds.
You asked for some favorite chemicals. I couldn't find the strobins, azostrobin, the fungicides that you'd not only find in the fields, but actually in drywall. They are in what's called purple drywall. And from a few years ago, I remember that they're extremely toxic to neurons in the dish, at least. And they seem to be coming up to be quite widely used, including in homes.
And could you repeat the class again?
They're called strobins, azostrobin, S-T-R-O-B-I-N, I think. But they have all sorts of names that end with strobin.
Thank you. Thank you.
Okay, how about we move to the third question in Dave's presentation then? If people had a chance to look at the list of not proposed for inclusion, and are there compounds that are listed there that in fact should be listed in one of the prior appendices? Any input on that? I can maybe start it off. So I noticed it seemed that one of the criteria was vapor pressure. Is something volatile or not? And if it's not volatile and you couldn't imagine a dust generating activity, it seemed that it didn't get listed. But it does seem, if you look at what's measured in the atmosphere, for example, you can find cocaine in particles. And cocaine is fairly non-volatile, but I think it's volatile enough that it can partition to the gas phase and then stick to a particle. So I would consider your volatility range maybe, and some of these things that are relatively low volatility are volatile enough that they can actually get up there and then partition to particles. So I don't know if you had a hard rule for a vapor pressure, but you may want to expand that range.
Yeah, we didn't have a hard one. We looked at combination of the number of carbons at times, the boiling point, the vapor pressure, all of those things, and tried to, in net, talk among staff and try to understand what we thought it would behave as. But that's a good point. Thank you. Yeah.
Yeah, I had been thinking about that too. I think that dust in general, specifically if they're in small sizes, if they're under PM10, really, they get transported, and so volatility is important. But I think as long as the particle size is small, it's going to be transported and should be included.
Now that you mention that, nanoparticles in general might be a category to look at, but things like carbon nanoparticles, nanotubes, nanofibers, those are in heavy industrial use now, so they may warrant being on the list.
And we did pick up, I think, one or two examples of that came from some of the IARC or other sources. We did pick up a couple of those. And yes, if anyone else has ideas on a way to structure or categorize them, we'd be open to that guidance as well. So far, we just took the way they were structured on one of these other 6 lists.
Any other panel comments on the third question or any of the other questions?
I have a methods question, technical question. So suppose a week from now, I have a chemical that I, thought about and double checked, and it's not currently listed, and it's not listed here. Is there one person, should we be feeding those to Jim, or they don't have to hear from a bunch of different people? It can be sort of collected together. Is there a conduit for such room comments?
So if you have that information between now and November 22nd, bring it to our November 22nd meeting. So, we will be meeting again to discuss this list, and we expect some public comments about this. And so we'll get those public comments, I think, a week or two before the meeting. So we'll have some time to look at the public comments as well. So we'll have a discussion of the public comments and any other ideas that panel members have about the 3 questions that Dave asked. So please, between now and the 22nd, look at those 3 questions, think about your favorite chemicals or your least favorite chemicals, and see if you have input on Dave on the 3 questions. After the 22nd, how should we get input to you, Dave?
So, I'm sort of envisioning the 22nd. We'll have some public comments and then additional feedback from you all. As far as what we're sort of envisioning is we are going to have a whole other separate public process when we do our regulatory update. We'll have public workshops, sort of initial comment, formal comment. So any additional comments could just sort of be submitted probably to Gabe or myself, and then we would incorporate those into our informal comment that we have during the during that rulemaking process. I think also as a sort of final step, after sort of hearing the different comments today, I think sort of in the recommendation piece, we'll have sort of the action item list that we were sort of in a sense, our homework to do in establishing a more comprehensive list. We can kind of talk about sort of recommendations were this, this, and this, and those were done, and then kind of write that up in a more formal way that maybe at the end of the November discussion or the next meeting we can have some sort of vote or something, whatever that equivalent is for this group. That sound?
Yeah, we can certainly talk about what that would be, but it would seem to me a list of the SRP comments may be enough, not necessarily having to vote as a group about.
Just wanted to. My board's used to voting, so I'm so sorry.
Well, we'll see how people feel about voting on the 22nd. Any other comments from the panel? Okay, so I've got a couple more small agenda items, but I want to give Jim a break. Okay, Jim's a Superman. He's going to continue. So just first, thank you to Dave, Gabe, Beth, for all your input and for allowing us to give you input. Next agenda item is some administrative matters. So first is for me to remind you that we're going to have the conference call in the morning of the 22nd. And then, didn't we have a time or no? We have not set it. Okay, thank you. So
It would be really good to set the time.
Yeah, 100%.
Because everybody wants, so we can get on our calendar.
You want to set the time right now?
Fine with
Or you
me.
want Jim to send an email right after the meeting? I think an email might be more efficient. But I hope everybody's blocked out the morning. That was what the email originally said, it'll be the morning of the 22nd. So
Well, I have a half hour that was pre-booked and I can't change, but
okay,
that happens.
yeah.
But before this was set.
Will that work for you, Jim? Okay, so Jim will send out an email. We'll nail down the time. Then the next meeting that we will do in person will be, it's tentatively set for February 27th, 2020. So make sure that's on your calendar. And Jim has already sent out an email about that as well. 27th. Next up, Administrative item, update on HDI, all right, hexamethylene diisocyanate. We considered our March 2019 meeting. The well for that has now been completed and adopted by OEHA, so that's set. Thank you, panel, for all your work on that. And that brings us to our last agenda item, which is both happy and sad. Happy for Jim, sad for us. So Jim Behrman is retiring after more than 20 years of service to the SRP and to CARB. So I know as chair, I'm going to miss him enormously because he's the one who actually knows what's going on. But we have somewhere, well, do we have Reed? Not have Reed. Okay. Reed has something on his person that I need, which is a letter of appreciation for Jim and all his service. So we're going to send out some scouts. No? I'm going to ask Jim if he can get in touch with Reed so that Reed can give me the letter so I can read it to Jim. Do you have Reed's number?
I do.
He didn't leave a folder, did he?
This is why you can't retire.
Right. This is a great example of what life is going to be like without Jim. And so panel members, after I read the letter, what we'll do is once the meeting's adjourned, we're going to take a picture with Jim. And then we'll get a copy of that picture to Jim as another token of our appreciation of all his service.
Maybe we should take the picture while we're waiting for Reed.
You know, that is an excellent point. Why don't we take our picture now?
Oh. Huh? I got a ride with Paul Blanc. You want to get a ride with Paul Blanc too, and he could.
You have to stop at Bart.
We could ask him.
You do that.
Oh, you'd have to ask Paul.
All right, everybody, we're back in action. Okay, so our last item of business is this letter from the California Environmental Protection Agency and the Scientific Review Panel to Jim Behrman in appreciation of all his service. And the letter reads, we wish to express our gratitude for your exemplary commitment and service to California's air toxics programs as the California EPA's liaison to the Scientific Review Panel on Toxic Air Contaminants for 19 years. The panel is responsible for the technical peer review of draft health risk assessments of candidate toxic air contaminants, new guidelines for the preparation of improved health risk assessments, summaries of the derivation of health values for other contaminants, and related documents. During your tenure, you assisted the panel in formulating dozens of formal notices and findings to assure their legal soundness and that all key points and conclusions were included. You also directed staff in the planning of panel meetings, which often involve challenging logistics, given the full schedules of panel members, timing needs of the state, and other factors. Your careful attention to the panel's needs, as well as to the scientific details of the documents under review, has enabled the panel to run smoothly and efficiently and to issue new findings and conclusions that have led to advanced health protective policies and measures. The end result is that we can all breathe cleaner air today. The details of the Scientific Review Panel's work and its contributions are critical to the development of state regulation and policy. Over the years, the panel listed 21 toxic air contaminants and 9 pesticide toxic air contaminants, and reviewed technical support documents for the Air Toxic Hotspots Program and the Air Toxic Hotspots Guidance Manual. The panel's independent, careful review of proposed actions, risk assessments, and guidelines assures the public, as well as the regulated businesses, that the scientific underpinning of the agency's regulatory work is sound. We thank you, Jim, for your service and your contributions in assisting the panel in improving the health of all Californians, and we extend our warmest wishes to you for a long and happy retirement. Sincerely, the panel. So we'll miss you a lot, Jim, but we're very happy for you that you're going to a happy place. With that, can I get a motion to adjourn? Oh, sorry. The guest of honor would like to, you have to speak into a mic for the record.
I just wanted to express my personal appreciation to the panel. This was just an unexpected gift. Thank you very much. But working with this panel just has been a nice, actually a second half to my career here. Having worked throughout the board starting several decades ago, it was a perfect way to close out. Wonderful place to work. Thank you all very much.
That's great. Thanks, Jim. I wish you the best in retirement.
I'm still going to be here until so I will see you. I will see you in November at the November meeting.
But that's a call-in.
Yes. Yes.
He'll talk to us on the 22nd. Yeah. Okay, with that, can I get a motion to adjourn?
So moved.
Can I get a second? Can we take a vote? All in favor?
Aye.
It's unanimous. Thank you all for your input on today's meeting, and we'll talk to you on November 22nd.
Station someplace?